Let us now start the unit of internal flow. This is one of the most important topics of entire fluid mechanics, and this is quite a lengthy unit. You are going to find 3 chapters inside this single unit, and there is very less to remember over here, and more logical concepts are going to be there. First of all, let us understand the meaning of what is internal flow. You see, in our subject, we are going to study 3 types of flow: internal flow, external flow, and open channel flow. Open channel flow is not a part of mechanical curriculum. Civil engineering, of course, you are going to have open channel flow. First of all, what is this internal flow over here? Internal flow can be defined as a flow through a conduit, a flow through a conduit, without a free surface, comma, which is driven by pressure gradient, This can be a simple definition of internal flow. So you are having a flow taking place through a particular pipe or a tube or a duct. Okay, conduit can mean any of these things, a pipe or a tube or a duct, such that the pressure difference is driving the flow. Such a flow is known as internal flow. Now, you can understand this internal flow by taking the difference between internal flow and open channel flow also. Open channel flow is a flow which is driven by gravitational force, whereas internal flow is driven by pressure forces. Take an example. Let us say you have a bottle of water. Now you want to drink water from here. There are 2 ways. One way is you take the bottle, you create a particular elevation difference for the bottle such that the water flows down. Such a flow is driven by gravitational force. It is caused by gravitational force. We call this flow as open channel flow. One more way, which generally we don't use, is let us say you take a straw, put in the straw and siphon off the liquid. Now how is the liquid coming up? The liquid is flowing through this particular conduit by the virtue of pressure difference. Inside your mouth, you are creating some kind of pressure and you are having some pressure inside the bottle. Due to the pressure difference, the flow is taking place. Such a flow is an internal flow. So let us do one thing. At this stage, let us write down some basic differences between an internal flow and open channel flow. Differences between internal flow and open channel flow. Sometimes we just mention open channel flow by OCF. Let us see what are the various differences you are going to have. Let us say internal flow over here and open channel flow over here. Imagine the cross section of flow. In the case of internal flow, let us say you are having a cross section such that throughout the cross section you are going to have the fluid present. The fluid is present throughout the cross section, so the entire surface of the tube or the conduit is experiencing wetness over here. Now come to open channel flow. In the case of open channel flow, let us say you are having a tube, but you are going to have a free surface over here. So let us say this is an example of open channel flow. So first difference you are finding is no free surface, no free surface in the case of internal flow. Coming to open channel flow, you're finding a free surface. You have to have a free surface. There is a free surface present in the case of open channel flow. This is the first difference we have. Second difference now. Second difference. Now imagine you are not having a free surface. What does this imply? This implies that the pressure is not always going to be atmospheric. It might become atmospheric in some cases. We are going to those cases also. But throughout the flow, you are not going to have the same atmospheric pressure. So I can say over here, pressure need not be atmospheric. Pressure need not be atmospheric throughout basically. Now if you see, since you are having a free surface, what should happen? We know that in the case of free surface, the pressure on the top is supposed to be zero gauge pressure or atmospheric pressure. So I can say over here that in this pressure throughout the free surface pressure throughout the free surface is atmospheric. Pressure throughout the surface has to be atmospheric. Next thing, extension of same point you can see. Now we know that the pressure forces are driving the flow over here. Therefore, throughout the pipe or the conduit, you are going to have variation in pressure. So I can say over here, pressure varies. Pressure varies throughout the flow. Pressure varies throughout the flow. So pressure has to vary throughout. Now coming to this case, since throughout the surface you are having atmospheric pressure, I can say that pressure throughout remains constant. Pressure throughout remains constant. Remains constant. Fine. Now last point, most important point, what is the driving force? We have already mentioned. In the case of internal flow, we know that the driving force has to be pressure force. So I can mention over here that flow is driven by pressure forces. In other words, you can say flow is driven by pressure gradient, variation in pressure that drives the flow over here. Coming to this case, in this particular case, flow is driven by gravitational force. Flow is driven by gravitational force. So it is the gravitational force that drives the flow. In other words, you can say flow is driven by elevation gradient. For example, if I have a certain slope, let us say I have a certain slope over here, I can assure myself in the case of open channel flow, the flow has to take place in this direction only. In the case of open channel flow should take place in this direction only. But if I'm having a pipe with a slope like this and the flow inside internal flow, it is possible the flow might take place downward or the flow might even take place upward depending on the pressure gradient. Let us take some examples. What are the examples in the case of internal flow? Very simple. You are having every flow through pipe every flow through pipe established flow through pipe has to be an internal flow. Now coming to an open channel flow. What can be the examples of open channel flow? You can have flow in canal, etc. are going to be examples of open channel flow. So this is regarding the basics of what is internal flow and what we are going to study. Probably for more than 10 hours, you are going to study only regarding this internal flow from here on. Fine. One thing you keep in mind that the concept of pressure gradient over here will be important. And pressure gradient can be understood just by this term over here, that is dP upon dx. dP represents change in pressure, dx represents some length along the flow. So x over here is the axis along the flow, it is the axis along flow. Now dP by dx over here basically represents change in pressure per unit length along the flow. Fine. This term will be the most important term throughout your subject of internal flow. After having seen the definition of internal flow, let us now talk about the classification of flow. You see, classification of flow is going to give us various chapters in this unit. You might have heard of laminar flow, turbulent flow, and so on. And for classifying this flow, a dimensionless number plays a very important role. The dimensionless number is known as Reynolds number. It is known as Reynolds number. It is represented by capital R, small e. Let us now talk about this Reynolds number. First thing, it is a dimensionless number. You will be seeing many more dimensionless number in the concept of dimensional analysis later on. But at this stage, this dimensionless number is important to us. It is talking about the ratio of two forces. Which two forces? Inertia force and viscous force. These two forces are important over here. So let me write. It is a dimensionless number representing the dimensional ratio of which two forces? Of inertia force to viscous force. Inertia force to viscous force. This can be the definition of your Reynolds number. Fine. So we'll be seeing sometimes viscous force will be more dominant. Such a flow will be called as laminar flow. Sometimes you'll be seeing that viscous force is so much dormant, it is very, very less, and that type of flow we are going to call as turbulent flow. Many more characteristics are there which will be dealt in detail later on. Right now just understand that these two forces are important and their ratio is more important to understand what type of flow is taking place. Let us now develop the formula of Reynolds number. You see, it is a dimensional ratio, so we have to look at the proportionalities of each of the forces. Let us start with inertia force. Force of inertia. All of us know that force of inertia is basically minus mass times acceleration. For the sake of simplicity, since we are just looking at the proportionality, let us neglect minus over there. Fine. It is mass times acceleration. I can write mass is basically density times volume. mass is density times volume. Let me mention like this. And acceleration is dv by dt. Acceleration is dv by dt, rate of change of velocity with respect to time, basic definition. Fine. So from here I can say, since volume is supposed to be proportional to a characteristic length cube, you take any volume, it has to be proportional to a characteristic length cube. And I know dv by dt can also be written as d2, I can write it as dv by, now look over here, dt can be written as, dt over here can be written as displacement per unit time, is it not? Sorry, what do you call, time can be written as displacement by velocity. So it's ds by dv, therefore d into dv over, let us say, into dv over here. So from here I can say dv upon dt is proportional to v square by L. You are seeing over here v square and ds is proportional to some characteristic length. Let us put those things over here. So I find force of inertia is proportional to density times, now volume means length cube, times dv by dt is proportional to v square by L. From here you can write that force of inertia is proportional to density into L square times v square. Let me save this as some equation number 1. Now let us look at the concept of force of viscosity. Force of viscosity is equal to how much? We know force of viscosity is equal to shear stress by the virtue of viscosity times shearing area. Shear stress by the virtue of viscosity times shearing area, which is going to be equal to mu into du upon dy. I am using Newton's law of viscosity over here, times shearing area, therefore as over here, shearing area. Now look over here, what can I do? I can write that du upon dy is proportional to how much? I can say it is proportional to velocity per characteristic length. So it is proportional to velocity upon characteristic length. And shearing area is proportional to length square. Keep this in your mind. So from here I can say force of viscosity is going to be proportional to mu into velocity per length multiplied to length square. From here you can say force of viscosity is proportional to mu VL. Force of viscosity is proportional to mu VL. Save this as certain equation number 2. Now we need to get the dimensional ratio of these two things. So from here I can write the value of Reynolds number. The value of Reynolds number is going to be equal to force of inertia upon force of viscosity. Force of inertia upon force of viscosity. We have seen that force of inertia is proportional to density into V square into L square, and force of viscosity is proportional to mu VL. From here we can say the formula of Reynolds number is given by rho VL upon mu. The formula of Reynolds number is given by rho VL upon mu. Rho VL upon mu. Rho is density, V is characteristic velocity, mu is viscosity. L is very important for us. L is known as characteristic length of flow. L is known as characteristic length of flow. Characteristic length of flow. Now, most of the time in our subject of internal flow, we are going to deal with pipe flow. In the case of pipe flow, the characteristic length is going to be diameter. So let me mention over here, this L is going to be equal to diameter in internal flow. It is going to be diameter in internal flow. So it is going to be diameter for not internal flow, rather pipe flow. Let me correct this thing. In pipe flow, not internal flow, it is rather pipe flow. Now, since it is diameter for pipes, I can say flow through pipes, for flow through pipes, flow through pipes, for flow through pipes, the formula of Reynolds number is going to take the shape of rho Vd upon mu. This is a formula we have worked with mostly for the case of flow through pipes. Moving further, let us classify the flow based on Reynolds number. You see, when the value of this Reynolds number, is going to be less than or equal to 2000, you are going to say such a flow in the case of flow through pipes is laminar flow. This is all for flow through pipes, please. It is going to be laminar flow. Now, if the flow exceeds the value of, if Reynolds number exceeds the value of 4000, we'll call such a flow as turbulent flow. We'll call such a flow as turbulent flow. Turbulent flow. In between these two, there is a changing phase or transition phase. Therefore, if the value of Reynolds number lies between 2000 and 4000, this phase over here is when laminar is shifting towards turbulent. So we call this flow as transitional flow. This as transitional flow. Fine. So these are the three flows in the case of flow through pipes. One more thing, it is not necessary that these only should be the rigid limits. It is possible that even some more value number beyond 2000 can also have laminar flow. Fine. And in some books you might find that this limiting value is going to be 2300. But as far as Indian textbooks are concerned and our examinations are concerned, please take the value of Reynolds number as 2000 only for laminar flow. Fine. In the case of flow through ducts also, moreover, this only is going to be the value. In the case of we are going to have different values, those we'll see later on. Moving further, after having discussed regarding the concept of Reynolds number, there is one thing which is very important in the case of internal flow, that is called development of flow or establishment of flow. Let us discuss this thing now. Development or establishment of flow. Establishment of flow. Development of flow or establishment of flow. I would recommend you refer to this topic again later on after you have finished the concept of boundary layer theory, because this becomes even more clear once you are having the idea of boundary layer theory. Let us see what is this development of flow or establishment of flow. Imagine that you are having a reservoir. To this reservoir you are having a pipe connected. Let us say something like this. Over here you have a reservoir. This, let us say, is a huge reservoir, and you are having a pipe over here. This is a pipe you are having connected to this thing. So the fluid is going to enter from the reservoir into the pipe. Please imagine this thing. Now, when the fluid is entering, initially what happens is the fluid velocities before touching the pipe are going to be uniform velocities. So initially, since you are having a flow taking place far away from a solid boundary, you are going to have uniform velocity profile. So this kind of velocity profile is uniform velocity profile. This kind of velocity profile you are having. The reason for this uniform velocity profile is, if you observe over here, there is no solid boundary at the periphery of this velocity profile. Therefore, you do not have any shear stress. Therefore, you are having a uniform velocity profile. Now, imagine logically that the moment these arrows are moving into the pipe, that is, the fluid particles are moving into the pipe, the peripheral arrows, by peripheral I mean these two arrows, let us say, for example, they are going to come in contact with the solid boundary. The moment they come in contact with solid boundary, by the virtue of no slip condition, now what happens? Viscous forces are generated. Viscous forces are generated. Once these viscous forces are generated, these velocities will become lesser and lesser. In order to compensate the loss in velocity over here and maintain continuity equation, what happens? The inner velocities will become more and more. Imagine this thing. I am having 3, 3, 3, 3, 3 everywhere. Okay. Logical concept. Everywhere you are having 3. The moment you enter, 3 has become 0, 3 has become 0. But I want the net value to be over here also. So who is going to compensate for that? The inner velocities have to develop so that the loss in velocity over here is compensated. You see, continuity equation has to be valid. Now, let us take any place over here inside the pipe. Near the wall, you are going to have some viscous region. Again over here, viscous region you are going to have. And inner portion, the inner in-between portion, you are going to have ideal flow or uniform velocity profile taking place. So let us now make a diagram of this viscous region. Let us say you are having this viscous region developed like this. Viscous region developed like this. Symmetry has been maintained place. Viscous region is developed. And inner region is going to be ideal flow region. Ideal flow region. Now, this viscous region keeps on increasing as you move forward, to the point that this viscous region will eventually merge. This viscous region will eventually merge. Let us say at this particular point, let us say at this particular point, the viscous region is merging. If you imagine the velocity profiles now, let us take the velocity profiles. One moment, please. I hope you have understood where viscous region is going to be there, where ideal flow region is going to be there. If you look at the velocity profile, let us say in this particular region, if you look at the velocity profile, the velocity at the boundary is going to be 0. The boundary velocities are 0. And the velocities are going to keep on increasing by the virtue of going to have something like this. Keep on increasing. In this ideal flow region, from here to here you are having ideal flow region, the velocity should be maintained as constant. Velocity is maintained as constant. If you say the center line velocity over here is capital U1 and the center line velocity over here is capital U. Let us say, for example, this is capital U2. Tell me logically which capital U1 has to be greater. U1, which capital U has to be greater, U1 or U2? The answer should be U2 should be greater. U2 should be greater. Center line velocity keeps on developing. Let us say at this particular point, if you look at the velocity profile. Now tell me, how much is the ideal flow region at that particular point? 0. Because ideal flow region was keeping on decreasing to the point it became 0 over here. If I look at the velocity profile at this particular section, I am going to have throughout this particular section a uniform velocity profile. A uniform velocity profile, sorry, a real flow velocity profile. I'm sorry, at that particular section, I'm going to have throughout a real flow velocity profile. Let us say this velocity over here is U3. It is U3. I can write over here U1 is less than U2 is less than U3. From here onwards, I'm going to have the same velocity profile being maintained provided the flow is steady. Provided the flow is steady, the velocity profile at every section is going to remain the same. Fine. After having understood this, now let us talk about the term development or establishment of flow. The flow taking place from the initial point till this particular point, is known as developing flow. It is known as developing flow. It is known as developing flow. And this particular region and this particular length of the pipe is known as establishment length. LE over here stands for establishment length. Establishment length. Establishment length, also called as entrance length. It is also known as entrance length. LE is known as establishment length or entrance length. The flow from here to here is known as developing flow. The flow has not matured completely. It is still in the developing stage. Every step forward, its velocity profile is keeping on developing to become completely real flow velocity profile. Are you following this thing? It is a mixture of ideal flow and real flow. Over here, purely real flow. Therefore, the flow in this particular region, is known as fully developed flow. It is known as fully developed or fully established flow. You can use any phrase, developed flow or established flow. Are you following this thing? I hope you are. So this is regarding the concept of entrance or establishment or development of flow. Remember, whatever we are going to study in our subject of internal flow is going to start only from here. Only from here. No equation we write is applicable in this particular region. So in this region, our equations are not applicable. The reason being, every equation we are writing is for a real flow case. Since it is for a real flow case, we are looking for a region where the flow has to be completely real, and that region is going to be the fully developed region. Moving further, we also over here have to mention regarding the relationship between the diameter of pipe and establishment length. You see this establishment length and the diameter of the pipe, both of them are having some relationships. Let us see the relationship. The relationship is given by the ratio. The ratio of establishment length to diameter. Establishment length to diameter. This value is going to be equal to 0.07 times Reynolds number in the case of laminar flow. In the case of laminar flow. and this very value of establishment length to diameter is taken as 50, even though in some cases it is a function of Reynolds number in turbulent flow also, but in general in turbulent flow we are going to take it as 50 in the case of turbulent flow through pipes, turbulent flow through pipes. So this is regarding the concept of Reynolds number and the concept of establishment of flow. Now what are we going to study in this internal flow topic? Strictly speaking, we are having only 3 chapters in internal flow topic, but I am going to break this down into 4 chapters. Let us see first of all the name of 3 chapters which we have. The 3 chapters are, first chapter is laminar flow, very famous name. Laminar flow is the first chapter. The second chapter is going to be flow through pipes. Flow through pipes. Very, very important chapter. Probably in this entire internal flow topic, the most important part is flow through pipes. This is the most important part. Fine. The last chapter you're going to see over here is turbulent flow case. Turbulent flow. These 3 chapters you are going to see in the case of flow through pipes. Sorry, internal flow. In internal flow, you will see these 3 chapters. Now, what I'm going to do, for the sake of simplicity, I will take some portion of flow through pipes and put ahead of laminar flow, and I'll call it a smaller chapter, very, very small chapter. Let us say fundamentals of internal flow. Fundamentals of internal flow. Internal flow. What are the basics of internal flow? We'll take some topics from here and put ahead over here. The reason is, let me tell you this thing, the reason is, these fundamentals are going to be valid throughout this particular topic, all these 3 topics. Since these fundamentals are valid throughout over here, let us beforehand study these things. So basically 3 chapters are being converted to 4 chapters. Strictly speaking, what you are seeing over here is part of flow through pipes only. So this becomes all the more important for you. This again is important for you. Only 5 or 6 points you are going to see in the case of fundamentals of internal flow. Very, very basic points. Probably some derivations also you are going to see. But once you understand that, these topics will become easy for you. Fine. So this is our flow chart in the case of internal flow. Till now what we have seen was the classification of flow based on Reynolds number. So we have mentioned that there are three types of flow. One is known as laminar, the other is known as turbulent. In between this laminar and turbulent, we are having a flow known as transitional flow. If the flows are different, the equation for each parameter also is going to be different. For example, let us say you are having a laminar flow. The equation for velocity in laminar flow is going to be different from the equation of velocity in turbulent flow. So every parameter is going to have different equations. But there are some equations which are common for all the flows. Our topic right now is dealing with those concepts. So let us say our topic's name is fundamentals of internal flow through pipe. Internal flow through pipes. Fundamentals of internal flow through pipes. In this, we are going to see some equations which are common for every internal flow through pipe, regardless of whether the flow is laminar, transitional or turbulent. Before we start, let us first of all discuss regarding when are these equations going to be valid. So the conditions required for validity of these equations we are going to see now. Let us say conditions required for the validity of these equations. There are two conditions required under which these equations are going to be always valid. The first condition required is the flow has to be steady. So let me mention over here, the first condition we are having is flow has to be steady. Has to be steady. If the flow is steady, only then the following equations we are going to write sometime later are going to be valid. Now what do we mean by steady flow over here? Flow being steady basically means that the discharge taking place through flow or to the pipe has to be a constant. It should not vary with respect to time. So you can see, let us say you are having a pipe over here of a constant cross section. You are having a pipe. Through this pipe you are having a discharge Q taking place over here. This Q should not be a function of time. This is what I mean by flow has to be steady. This is the first condition. The second condition, again important condition. The second condition is the flow has to be fully developed. Flow has to be fully developed. Fully developed. If the flow is fully developed, only then our following equations are going to be valid. We have already discussed regarding the concept of development of flow or establishment of flow, where we have mentioned something known as fully developed flow. Now let us see what are the various parameters we are going to discuss in our topic right now. There are going to be 5 parameters. There are going to be 5 parameters and correspondingly 5 equations we are going to have. The first parameter we are going to see over here is known as equation governing internal flow through pipe. Internal flow through pipe. Internal flow through pipe. This is the first parameter we are going to discuss. Fine. After having discussed this equation, in this equation you will be finding there are 2 parts. One part deals with pressure, the other part deals with shear. So our second equation is going to deal with pressure, and in pressure it is going to be pressure drop. So our second equation is regarding the concept of pressure drop. Now before I start discussing about this, let me give you an idea why the pressure is dropping along the flow. You see, whatever we are discussing over here is real flow. If the flow is real, for sure there has to be some loss in head. If there is a loss in head, amongst the three heads someone has to sacrifice. You see, the velocity head will not be sacrificing. The reason is cross section area is same. If cross section area is same along the length, then I can say that velocity at every section by continuity equation also is same. So velocity head is not sacrificing. Let us say the datum of a particular pipe is remaining constant. So datum also is not sacrificing. The only head that is going to sacrifice is going to be the pressure head. Correspondingly, there has to be pressure drop along the flow. If I am having a pressure at the initial section, at the later section I am going to have a lesser pressure. That is what is meant by the pressure drop over here. Then the third thing we have over here, see bit, let us say, very important thing, probably the most important of all these equations, and that is shear stress. Shear stress. Again, why is shear stress developed? If you ask me, I would straight away tell that the flow is real, therefore the velocity profile at any section is not going to be a uniform velocity profile. If you have a non-uniform velocity profile, du by dy is going to be developed. Eventually there has to be some development of shear stress. Next point, let us say point D over here. This point D over here. By the virtue of shear stress, there is going to be a topic known as friction coefficient and friction factor developed. So let me write over here, fourth point over here is friction coefficient and friction factor. Friction factor. Friction coefficient and friction factor, we'll be seeing that in detail later on. Finally, you're having one more point, very important point. This point is known as major head loss. Major head loss. It is known as major head loss. Fine, we are going to have two types of losses in any flow. One is known as major head loss, the other is known as minor head loss. We'll be discussing the details of these losses later on. But over here in our topic today, we are going to discuss the equation of major head loss. So this is regarding the idea of fundamental equations in any internal fluid flow. Fine, these equations require, again I'm telling you, these equations require two conditions. One is the flow has to be steady, the flow has to be fully developed. Now let us start the first bit. If you remember, it was equation governing internal flow through pipes. Internal flow through pipes. Flow through pipes. Equation governing internal flow through pipes. Very simple equation. We are going to do the derivation now. If you find some difficulty in the derivation, at least try to remember the end result over here. What we are going to do now is we are going to derive the equation for a horizontal pipe. At the end, I will tell you how to manipulate the equation if the pipe is having some inclination. So let us take a horizontal pipe over here. Imagine you have a pipe. suppose something like this. This is a pipe, let us say. Let us take the center line over here. Assume this is the center line of the pipe over here. Now, I'm supposed to choose a differential fluid element over here. My differential fluid element requires me to understand what are the various axes in the flow which are governing the flow. Let us see the various axes which are governing the flow over here. One thing I can say is, I am having one axis, let us say I am having an axis which is perpendicular to the centroidal axis. This axis I am going to call as radial axis. This axis I am calling as radial axis. Then I have one more axis. The other axis is along the flow. Let us say this axis over here I am calling as x-axis. So my flow is defined by two axes over here. One is r, the other is x. So let me write over here. R over here is radial axis. R is radial axis. The other axis is x. X is axis along the flow. Axis along the flow. Now, don't think that x-axis is only represented in the horizontal direction. Please understand that if I was having a pipe something like this, the x-axis would be present in this direction. This would be my x-axis. So x is an axis along the flow, regardless of whether it is horizontal, inclined or vertical. If the pipe is vertical, even the x-axis should be vertical over here. Please understand this thing. Moving further, now I have to choose a fluid element. My fluid element is supposed to have over here a dr as well as a dx. That means a small part in radial axis as well as a small part in axis. And this type of fluid element is going to be a hollow cylinder. Let us say I choose over here a hollow cylinder. I choose over here a hollow cylinder, something like this. This is a hollow cylinder. Suppose this hollow cylinder is such that its internal radius is r. This is the internal radius, that is r, and the thickness over here, let us say this thickness over here, is dr thickness. So let me mention over here this thickness as d thickness, and the length of this element is dx. If you have difficulty in understanding, let me expand this diagram so that you can see this easily. So I have chosen a hollow cylinder. The hollow cylinder is having internal radius, which is hollow part, as r, the thickness as dr, and the length of the fluid element I have chosen is equal to dx. Now, on this fluid element, I am going to apply two equations. One is continuity equation, the other is momentum flux equation. Let us say I choose two sections over here. One section is the initial section over here. Let us say this is section 1. The other section is the final section over here, section 2. Both these sections are having same cross section area. So I can say A1 over here is equal to the cross section area in both sections is same. If cross section area is same, it straight away implies that by continuity equation V1 has to be equal to V2. The velocity at section 1 and the velocity at section 2, both of them are same. Let us say this is V1 and this is V2 over here. Both the sections are having same velocity. Keep this in mind. Now I am going to apply momentum flux equation. So let us do one thing. Let us say by momentum equation or momentum flux equation, we know that value of summation of force in a particular axis has to be equal to delta m dot into velocity in that particular axis. This is the equation we have. So let us do one thing. Let us again draw the diagram of our fluid element in the form of a control volume. So that diagram is going to be something like this. Let us say let us say this is our control volume I'm having. Let me mention over here, this is my control volume. This is section 1, this is section 2. We have already mentioned that the velocity at section 1 and section 2, both of them are same. That means this value, which is supposed to be equal to m dot common to V2 minus V1, must be equal to 0. Is it not? Delta m dot into velocity in x would mean m dot into final velocity is V2, initial velocity is V1. So V2 minus V1, that is equal to 0. This ultimately is implying to me that in this control volume, the summation of force in x-axis has to be equal to 0. The net force in x-axis must be equal to 0. I hope you have followed till here. Now our next aim is to identify what are the various forces acting in x-axis. Let us see the various forces acting in x-axis. At section 1, the first thing I am going to represent is the pressure force. Let us say over here I am having certain pressure force. So what I am going to do is I am going to write over here P times what is the area it is acting over. The area it is acting over, this annular area over here, it has to be equal to 2 pi r times dr. So let me write 2 pi r, one second. The pressure force is P times 2 pi r times dr. This is the value of pressure force acting over here. At section 2, let us say the pressure is different. The pressure over here is different, let us say. So I am writing the pressure is equal to P plus dP. This is the pressure force, let us say. And what is the area it is acting over here? Exactly same area. That is again 2 pi r times dr. Exactly same area. So pressure forces are done with. Any other force acting over here? Yes, one force, and that is shear force. You see, the inner surface and the outer surface, both of them are going to experience shear force. So let us say this is inner surface and this over here is outer surface. Outer surface. Now you have to decide in what direction are these shear forces going to act. I'll help you with this, but please answer me while I'm doing these things. Tell me, if there is a fluid element at the inner portion, is it going to have higher velocity or lower velocity compared to our element? The answer should be higher velocity, because over there the fluid element is closer to center Therefore, velocity has to be higher, is it not? If the inner fluid element is moving faster, where is it going to shear our element? For sure, it is going to shear our element in the forward direction. So over here, you are going to have shear force in this direction. Now come to the lower part or the outer part. If there is a fluid element over here, this fluid element, let us say, it is going to move faster or slower with respect to our element. For sure, it is going to move slower because it is closer to the wall of the pipe, is it not? If it is moving slower, that means it is trying to drag our element in the backward direction. Therefore, the shear force over here has to be in this direction. It has to be in this direction. I hope you are following the direction of shear. Now, next thing is, I am supposed to write down how much is this shear force going to be. So let us say this shear over here is tau at some radius r. Shear stress is tau at some radius r multiplied to the surface area. Imagine the surface area, please. The surface area is going to be this internal circumference multiplied to this length. Internal circumference is 2 pi r, length is dx. Therefore, I am supposed to write over here, excuse me, I am supposed to write over here into 2 pi r times dx. 2 pi r times dx. I hope you are following this thing. This is a surface area. Now come to this shear. The shear stress over here is tau at r plus dr. A different shear stress, let us say. Tau at a radial distance, that is equal to r plus add to it one more dr. Fine. Multiplied to how much area? Multiplied to how much area? The area is supposed to be 2 pi times the radius for this outer circle is r plus dr multiplied to length is again equal to dx. This is the value we are having. So now our control volume diagram is perfect. What is the next thing we are supposed to do? We are supposed to put all these forces in the equation summation of force in x equal to 0 and get some result. Let us see how do we do that. One moment please. I am writing all these things now in the equation summation of force in x equal to 0. This is equal to 0. We have already deduced this equation. Now let us start writing. First thing I am going to start with is this force. It is this force. Therefore, let us say I have over here P times, excuse me, P times 2 pi r times dr. Fine. Second force is going to be this force. So minus of P plus dp times 2 pi r times dr. Fine. Next thing, I am going to write the shear. I am starting with the inner shear first. It is in the positive direction. So let us say plus tau at r multiplied to 2 pi r times dx. 2 pi r times dx. And next thing I am having is this in the opposite direction. So let me write over here minus tau at r plus dr multiplied to 2 pi r, excuse me, 2 pi r plus dr times dx. this entire thing has to be equal to 0. Please observe the equation once if you are having any difficulty. I am repeating the equation. The first two terms are for the pressure terms over there. One is positive, one is negative. The next two terms are for shear stress over here. I hope the equation is clear. Please pause the video if you have any difficulty in understanding the equation. What next am I going to do? Now I am going to keep the pressure terms on one side and shear terms on the other side. Acha, before that, one more thing. Before that, I can straight away cancel off one thing. You see over here, P times 2 pi r dr. P times 2 pi r dr. So let us say I cancel this off. So I remain over here with minus of dp times 2 pi r times dr has to be equal to. Now let us put the shear terms on the other side. If I put the shear terms on the other side, I am going to have over here tau at r plus dr multiplied to 2 pi into r plus dr times dx. That is, I have chosen this term first. Next, minus of tau at radius r multiplied to 2 pi r times dx. 2 pi r times dx. Fine. Let us further write this as, minus dp into 2 pi r times dr is equal to. Now this is going to be slightly tricky. Please understand this thing. I am taking 2 pi times dx common. 2 pi times dx common. What am I remaining with? I am remaining over here with this and this over here. This and r over here. So what I will do is, I will club these two things as tau times r at a position r plus dr. Is it not? This is tau and this is radius. At what location? R plus dr location. Similarly, I have over here tau times radius. At what location? R location. This is the value I am having. Fine. Now let us do one thing. Let us cancel off 2 pi on either side. Let us further say we are dividing over here by dr times dx. We are dividing by dr times dx. So what will we remain with? If I divide with dr and dx, then I'm going to have over here this r aside multiplied to minus dp upon dx. Minus dp upon dx is equal to, dx cancels off. I have over here tau times r at r plus dr minus tau times r at r whole divided by dr. Now if you are having basic idea of first principle of differentiation, this term over here is representing the rate of change of tau times r with respect to radius. You see over here, f of x dx minus f of x divided by dx, something very similar you are having. So now I can replace this entire thing by the term. Therefore I am supposed to get from here r into minus dp upon dx is equal to d by dr of r times tau. This is the ultimate equation which is governing the internal flow through pipe. This is the equation governing the internal flow through pipe. So let me save this as some equation A. If you remember previously I mentioned A bit as governing equation, so I am representing as equation A. Now before you stop over here, let me tell you one more thing. This equation is having a term over here P. It is having a term P, sorry, rather dP I am having over here. But strictly speaking, the term should not be dP by dx. The term over here should be R into minus dou P by dou x. This must be equal to dou by dou R of R times tau. This is how the equation should be. But still we are going to use this equation only. Why? Because the actual equation represents local pressure. That means pressure at any random location in your pipe. Fine. But this P over here is representing the average pressure throughout the cross section. So let us say this equation over here says P is average pressure at a cross section, whereas in this equation P is local pressure. That means that if I have a pipe, let us say I have a pipe. In this equation I am looking for variation of average pressure with respect to x. That means I take this section's pressure as, let us say, P1. How is it differing with some pressure P2 over here over a length of dx? This is what I am saying when I am talking about dP by dx. Whereas what does dou P by dou x mean over here? It means that I have chosen a particular location's pressure. Please understand, this is representing throughout the section's pressure, whereas this is representing a particular location's pressure, and at the same level how is it differing with the pressure somewhere forward by a distance of dx. That is why I call this as the equation for average pressure and this equation for the local pressure. But don't worry, most of the time we are going to use this equation only. So concluding, I can say that the equation we are having over here is R into minus dP by dx equal to d by dr of R times tau. After having seen the governing equation, the next thing we are going to see is regarding the concept of pressure drop. So let me write over here B bit. Pressure drop over here. Now regarding pressure drop, you have to understand few points first of all over here. The first point that is important to understand over here is pressure decreases linearly along the length of flow, Very important point. If you understand this, whatever mathematics I am going to do now will become extremely easy for you. First thing, you have to understand that pressure decreases, it does not increase. Of course, pressure has to decrease, the head has to decrease, total head decreases. Next thing, how does it decrease? It decreases linearly along the length of flow. This implies that pressure is going to be proportional to minus x power 1. Minus over here represents decrease, power 1 over here represents linear decrease. I hope you are following this thing. Minus is the representative of decreasing and power 1 is the representative of linear decrease. Now what happens from here? I can imply that, let us say, pressure is equal to some constant C multiplied to minus x. For example, let us say something like this. If it is so, let us say, and let us do one more thing. To be perfectly correct, I can say, let us say, plus C2, C1 times minus x plus C2, something like this is possible. This implies that the value of dP upon dx has to be equal to how much? Very simple. It has to be equal to minus C1. dP by dx is going to be some minus C1, where C1 is a constant, but minus C1 basically implies that dP upon dx is a negative constant. It is a negative constant. If it is negative constant, from here I can conclude that minus d upon dx minus dP upon dx should be a positive constant. It should be a positive constant. Why am I stressing on this thing? The reason is, in the previous governing equation, you have seen something like this. You have seen that R into minus dP by dx is equal to d by dr of r times tau. You have seen this equation. In this equation, this term over here, it might be deceiving that it is negative, but in reality it is a positive term. Moreover, it is a constant term. So minus dP by dx over here has to be a particular constant. We are going to discuss more about this thing. This term minus dP by dx is going to be a constant. That too, what kind of constant? A positive constant it is. Fine. After having understood here, let us now talk about the drop in pressure. Let us say you are having a certain pipe over here. You are having a pipe, and on top over here I am drawing a graph. Excuse me. I am drawing a graph. Let us say this is x-axis, that is the axis along the center line of the pipe, x-axis, and this over here is pressure axis. Let us say at some location x1 location, that is initial location of x, I am having a certain amount of pressure. At some location over here, x2 location, let us say this is x2 location, this is x1 location, I am having a value of pressure which is lesser, and the pressure is decreasing linearly. Let us say the pressure is decreasing linearly over here. Pressure is decreasing linearly. Let me say this pressure over here is equal to P1 pressure, and the pressure over here, this pressure over here is equal to some pressure P2. Between these two, I am having a distance, let us say L. Please understand this diagram. I have taken a pipe, I have decided two locations over here, random locations. At location 1 I am having pressure P1, at location 2 I am having a lesser pressure P2. The distance between these locations is L and the pressure along this length is dropping linearly over here. Fine. Now let me define this drop in pressure or pressure drop. Pressure drop in this particular case is equal to initial pressure minus final pressure. Initial minus final pressure, that is P1 minus P2. And we are going to represent this P1 minus P2 as delta P. We are representing it as delta P. In general, we have a habit of representing final minus initial as delta. But in this particular case, we are representing initial minus final as delta. So please be careful over here. So this is delta P. Fine. Now, if you observe for linear variation, I can say that the value of P2 minus P1 upon L, that is P2 minus P1 upon L, the distance between these two is, this distance is equal to L, has to be equal to, since it is a linear variation, it has to be equal to dP upon dx also. It should be equal to dP upon dx. From here I can also say P1 minus P2 upon L. Please observe what change I have made over here. I am just shuffling these two things. This must be equal to minus dP upon dx. It must be equal to minus dP upon dx. From here I conclude that wherever I see minus dP upon dx, I can replace it by delta P by L. The reason is this value is equal to delta P. I hope you are following this thing. Minus dP by dx is representing basically the drop in pressure taking place per unit length of the pipe. It is representing how much pressure drop is taking place per unit length. So coming back to this equation over here, this equation is representing radius multiplied to this term over here. Let me write this term as drop in pressure per unit length. It is representing drop in pressure per unit length. Radius multiplied to drop in pressure per unit length, which is a positive constant, has to be equal to the rate of change of r times tau with respect to radius. So the concluding thing I can say over here is, the concluding remark I can say over here is, first of all, minus dP upon dx is a constant value. Furthermore, it is a positive constant value. It is a positive constant value. This is the first point. Second point, I can say that wherever you are going to see next time onwards minus dP by dx in internal flow through pipe, mind you, in internal flow through pipe, wherever you see minus dP by dx, you can replace it by delta P upon L. Fine. This is regarding the concept of pressure drop. After having seen pressure drop, let us now talk about the next parameter. The next parameter I regard personally as the most important of all the parameters, and that is shear stress. And mind you, at the end we are also going to have a shear stress profile, extremely important for your examinations. So let me start over here. Seabed shear stress. shear stress, I represent it by tau, standard representation tau. How to understand regarding the shear stress? Go back to the governing equation. The equation said that R into minus dP upon dx is equal to d by dr of R times tau. This was the equation we got. So R into minus dP by dx is d by dr of R times tau. Forget about this minus dP by dx. Just now we have mentioned it is a positive constant. So if it is a constant, then what I can do is, I can write this equation as d of R times tau has to be equal to, d of R times tau has to be equal to minus dP upon dx times R into dr. This is the equation I am having. Now let us integrate these things. Let us integrate these things. I know that when R is equal to 0, when R is equal to 0, the value of R times tau also should be equal to 0. And I know that when R is equal to some random radius R, the value of R times tau, let us say, is R times tau. So this is the equation I'm having. After integration, what am I going to get from here? I'm going to get from here R times tau has to be equal to minus dP upon dx times R square by 2. Minus dP by dx times R square by 2. Let me cancel off one R from here and one R from here. If I cancel these two things off, now I get a more refined equation which says that tau has to be equal to minus dP upon dx times R by 2. This is the equation we have got. Let me save this equation as equation C. This is the equation of shear stress in any flow, be it laminar, transition or turbulent. As long as the flow is steady and the flow is fully developed, I am going to have this equation. Shear stress is equal to this constant value multiplied to R by 2. From here, what can I conclude? Let us write some statements of conclusion from here. Tell me, is shear stress increasing with respect to radius or decreasing with respect to radius? You will observe over here, I am having a minus dP by dx, which is a constant, positive constant. And you are having over here tau proportional to positive R, not negative R now. This entire thing is positive constant, therefore positive R. And that to R power 1. So from here I can conclude that shear stress increases. And what kind of increase? Linear, parabolic, hyperbolic, what kind of increase are you having? You are having over here a linear increase, linearly with respect to radius. So two things important over here. One is increase. Second, what kind of increase? Linear increase with respect to radius. If it is increasing linearly with respect to radius, then I can say at maximum radius the value of shear stress also should be maximum, and maximum radius is attained at the wall of the pipe. So now I can say at the wall of the pipe, at the wall of the pipe, at the wall of the pipe, the shear stress you are having is represented by tau naught. It is represented by tau naught. This tau naught is known as wall shear stress or boundary shear stress. Wall or boundary shear stress. Very important shear stress. And the value of radius has to be equal to capital R. So let us say in place of tau, if I put tau naught, in place of R I have to put capital R. Now the equation over here becomes, tau naught is equal to minus dp upon dx times capital R by 2. This is the equation of wall shear stress in the case of internal flow through pipe. Fine. From here you can also see that the value of tau upon tau naught will be equal to R upon capital R. The value of any shear stress, that is random shear stress to wall shear stress, is equal to corresponding radius of tau to the capital R. Fine. After having seen all these things, what I'm going to do now is I'm going to draw shear stress profile. So let us draw over here shear stress profile. Important bit. Shear stress profile. Very important for examinations. We know that it is linear, so let us draw a pipe first of all. Suppose you are having a pipe over here. Let us say a center line over here. At the center, let us take a section otherwise. First of all, let us take a section. This is the section I have chosen. At the center, the value of shear stress has to be equal to 0 because radius is 0. Then from here onwards, it is increasing linearly. Let us say tau is increasing linearly over here. There has to be a sense of symmetry. If you are not finding in my diagram, please don't mind. Draw it in a symmetric form. So let us say at any random radius R, the shear stress you are having is equal to tau. At capital R radius, the shear stress you would be having is equal to tau naught, right? The value of this tau upon tau naught is equal to corresponding radius by capital R. This is regarding the concept of shear stress and the concept of shear stress profile. Fine. Immediately after seeing the concept of shear stress, let us move over to the next concept that is known as friction coefficient and friction factor. So this over here is my D bit. Friction coefficient and friction factor. Friction coefficient and friction factor. I'm going to give you a statement now which is valid for the entire fluid flow, not only in the case of internal flow. This equation I'm going to see again in boundary layer theory also. Let me write the statement first. The statement is the ratio the ratio of wall shear stress to dynamic pressure wall shear stress to dynamic pressure is known as friction coefficient. Please remember this statement. So friction coefficient in our subject is the ratio of wall shear stress to dynamic pressure. So let us say if I am looking for friction coefficient, it has to be equal to, what is this wall shear stress represented by? It is represented by tau naught. And what is dynamic pressure? I hope you all remember what dynamic pressure is. We had a discussion on this thing. Dynamic pressure is half rho v square. Dynamic pressure is half rho v square. Now this statement and this equation over here is not valid only for internal flow. Let me tell you, it is valid for any flow, be it even external flow. In the case of boundary layer theory, in the case of drag and lift, over there also you can have this statement valid. But in the case of internal flow, through pipe, the name of this friction coefficient is a very specific name. It is called as Fanning's friction coefficient. So now let us write something which is specific for internal flow. Let me write over here. For internal flow, this F over here is known as friction factor over here is known as Fanning's friction factor. So we are having Fanning's friction factor, friction coefficient, not factor, friction coefficient, Fanning's friction coefficient. This Fanning's friction coefficient is represented by F prime or F dash, you can say, okay, F prime. And what value of this F prime? Just now we have seen it is supposed to be equal to tau naught upon half rho v square. So this is the equation for friction coefficient. It is known as Fanning's friction coefficient equal to tau naught upon half rho v square. Fine. So remember this thing. The word Fanning's is used only for internal flow. You are not going to use this again later on in the case of boundary layer theory. Over there we'll be calling it a skin friction coefficient. Now there is one more thing which is known as friction factor, and this friction factor is 4 times the Fanning's friction coefficient. And this friction factor has a very special name in internal flow. It is called as Darcy friction factor, very famous term. So let me mention over here something known as Darcy friction factor. Darcy friction factor, very important term, Darcy friction factor. This Darcy friction factor is given by, it is given by F, and the value of Darcy friction factor F is equal to 4 times F prime, or you can say it is equal to 4 times tau naught upon half rho v square. This is the value of Darcy friction factor. So we have seen 2 things, very small terms over here. One is Fanning's coefficient friction, and that is tau naught upon half rho v square. 4 times times Manning's coefficient of friction is equal to Darcy friction factor. After having seen the concept of friction factor and friction coefficient, let us now start the final term and very important term known as major head loss. Major head loss. Major head loss in internal fluid. Let me tell you that there are two types of losses. One is known as major head loss, the other is known as minor head loss. We'll be studying these losses again in detail. At this stage, it is sufficient if you understand that major head loss is by the virtue of friction or friction losses. Minor head loss takes place due to geometric changes in a flow. Now, for this major head loss in internal flow, let us develop the equation by considering a pipe. Imagine there is a pipe of uniform cross section. Let us say it is having a uniform diameter. Suppose the diameter is equal to capital D. Through this pipe, let us say there is a flow taking place, an internal flow is taking place in the upward direction, and I consider this direction as positive x direction. Let us say this is x direction I am having. Now what I do, I choose a portion of the flow for studying purpose. Let us say I have over here a section I am choosing this much of section of the flow. Let us say this is certain section, section 1, this is some section, section 2 I am having. Let us say at section 1 the velocity is equal to v1, at section 2 the velocity is equal to v2. What can I say regarding these two velocities? I can write over here by continuity equation, the value of A1 V1 has to be equal to A2 V2. Since the diameter is a constant, I can cancel off A1 and A2 over here. From here I can conclude that the value of V1 has to be equal to V2. Let me save this equation over here as equation number 1. I am saving this equation as equation number 1. Next thing what I am going to do is I am going to write down Bernoulli equation between these two sections. So I can say by Bernoulli equation, I know that the value of P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2 plus head loss. This is the equation we are having. Now you see the value of V1 square by 2G and V2 square by 2G, both of them are same, since we have established already V1 is equal to V2. So now I can say from here that the value of head loss is equal to P1 minus P2 by gamma plus Z1 minus Z2. So let me save this equation over here as some equation number 2. So these are two equations I'm having. Now to understand this value of head loss further, what I'm going to do is I'm going to apply momentum flux equation. For applying momentum flux equation, let me do one thing. Let me drag this diagram somewhere below so I can study it further. Now let us say I choose a reference datum over here. I am choosing a reference datum over here. Let us say z over here is equal to 0. After choosing this reference datum, let me take this section 1 over here. Let us say this value of datum head is equal to z1. This value is z1, and this value of datum head, let us say, is equal to z2. We are having z1 and z2. Fine. Let us further say that the length over here between these two is equal to capital L. This length between the sections is equal to capital L. For writing the momentum equation, I need to know all the forces involved. For knowing all the forces, let us start first of all with the pressure force, the most basic force, the pressure force over here. I know that at this section there is going to be some pressure intensity acting in this direction. Let us say it is equal to P1. Likewise, I am having a pressure intensity over here. Let us say it is equal to P2 I am having. Fine. Apart from these pressure forces, I am going to have a force by the virtue of weight. By the virtue of weight, I have a force, let us say W coming down. Apart from this, there is going to be one more force, very important force, that is a frictional force over here. Imagine that the flow is taking place in the upward direction. Where is the surface going to provide the friction? In the downward direction or upward direction? Of course, in the downward direction. So therefore, I am having a frictional force acting in the downward direction over here. The intensity of this frictional force is some shear stress tau naught. I hope all these things are clear to you. Let me assist my diagram with one more thing over here. Let us say the angle of inclination over here is equal to theta. It is equal to theta. Now I want you to help me with something. Tell me, what would the angle over here be equal to? This angle would be equal to how much? Imagine a virtual right angled triangle. Right angled triangle. If this angle is theta, a virtual 90 degree over here, this angle would be equal to 90 minus theta. So what component of W would be coming in this direction? The component should be equal to W cos 90 minus theta or sin theta. Fine. I am having W sin theta in the downward direction. One more thing. Please give me the value of L in terms of Z1 and Z2. Z1 and Z2, give me the value of L. For that, I will do a small change in this diagram that we will delete later on. Let us say I create this triangle. Okay. In this triangle, you know that the distance from here to here is equal to L. The vertical distance is equal to Z2 minus Z1. Z2 minus Z1. And this angle over here is equal to theta. So tell me, in this particular triangle, let me do one thing. You are having certain triangle over here, a triangle over here. This is equal to L. This is equal to Z2 minus Z1, and this angle is equal to theta. From here you can say that the value of Z2 minus Z1 has to be equal to L times sin theta. It is equal to L times sin theta. So everything is established in this diagram. It is only about applying this in the equation. Let us start writing the momentum equation now. I know by momentum equation that summation of force in x-axis has to be equal to delta m dot into velocity in x-axis. This is the equation we have. Now, the value of velocity in x-axis final is equal to v2 and x-axis velocity initial is equal to v1. We know that the value of v2 and v1, both of them are same. If both of them are same, we can say that delta m dot into velocity in x-axis has to be equal to 0. M dot into velocity in x-axis has to be equal to 0. If it is so, from here I can conclude that the value of net force in x-axis must be equal to 0. Now let us write this equation. What are the various forces acting in x-axis? I have chosen the upward direction as positive x. Please help me now. First term is going to be P1 times its area. So therefore I have over here P1 times. What is the area it is acting over? It is acting over an area of pi d square by 4. Fine. Next term is P2 times area, but this is a negative direction. So let us say minus P2 times pi d square by 4. Next, you have a component of weight in the downward direction. Therefore, I can write over here minus W sine theta, minus W sine theta. And finally, you are having a component of force by the virtue of wall shear stress in downward direction, that is tau naught multiplied to shearing area. So let me write over here minus tau naught multiplied into shearing area. This entire equation has to be equal to 0. This is the equation we are having. Now please answer me, what is the value of shearing area over here? If you want to look at the diagram, tell me what is the value of shearing area over here. Shearing area should be equal to cross section multiplied to length, is it not? So I can write over here the value of shearing area is equal to cross section, circumference of the cross section, that is pi times d multiplied to L. Acha, one more thing. Let me do one more thing over here. I can say the value of weight has to be equal to gamma times volume, correct? And that has to be equal to gamma times volume is equal to pi d square by 4 times length. This has to be the value of weight. Let us put the value of AS and W like this and write this equation again. If I write this equation again, let us say rewriting this equation over here, I have P1 minus P2 whole multiplied to pi d square by 4 minus, in place of W let me put this thing, so gamma pi d square by 4 times L, this is W multiplied to its sine theta. Sine theta has to be equal to tau naught multiplied to AS. AS is equal to pi d L. This is what we have. I hope this is clear to all of you. Now let us recall something we have studied in the previous topic. We know that the value of tau naught upon half rho v square is equal to F prime. It is equal to F prime, Fanning's friction coefficient, or I can say it is equal to F divided by 4. F prime is Fanning's coefficient of friction and F is Darcy friction factor. Let us do one thing. Let us take this half rho v square and push it over here. If I put it over here, then what do I have? I have tau naught is equal to F by 4 into half rho v square. Let us do one thing. We'll take this value of tau naught and place it over here. So what do I have now? The equation changes to P1 minus P2 whole multiplied to pi d square by 4 minus gamma pi d square by 4 into L sin theta has to be equal to F by 8 into rho v square times pi dl. This is what we have. This is an equation we are having. What I'm going to do next, I'm going to divide this equation throughout by gamma into pi d square by 4. If I divide this entire equation by gamma pi d square by 4, what am I left with? I have over here P1 minus P2 whole divided by gamma minus L sin theta has to be equal to F by 8 density V square pi dl. Now you see, dividing by something is as good as multiplying by inverse. So let me say multiplied to 4 upon gamma pi d square. Now look at this thing. What is this going to be? This is going to be equal to P1 minus P2 by gamma minus L sin theta we are having. Now you see, L sin theta we have seen some time back. What was the value of L sin theta we have seen? Look over here. L sin theta was equal to Z2 minus Z1. So I can write over here, I can write over here in place of L sin theta Z2 minus Z1. Z2 minus Z1. And look at this term over here. This term you look over here. I cancel a 4 over here. I get a 2 over here. Density cancels. G means pi and pi cancel. 1D cancels with 1D over here. So what do you have? This is equal to FLV square upon 2GD. This is equal to FLV square by 2GD. If you look at this term, sometime back we have saved an equation as equation 2. This is basically representing your head loss. So from here we get head loss is equal to FLV square upon 2GD, or you can also say it is equal to 4F prime into LV square upon 2GD. This is the equation of head loss we are having from here. This is a very, very important equation. It is known as Darcy-Weisbach equation. It is known as Darcy-Weisbach equation. It is known as Darcy-Weisbach equation. So this is the equation which represents major head loss in the case of internal flow through pipe, regardless of whether the flow is laminar, transition or turbulent. Let us now summarize whatever we have seen. This will be important for your short notes. Summary of what we have seen. In total, we have seen 5 equations. Let us quickly write them down. The first equation was the governing equation. Equation governing the flow. Governing the flow. And what did this equation say? It said that R into minus dP upon dx is equal to d by dr of r times tau. This was the equation governing the flow. The second thing we have seen was regarding pressure drop. Pressure drop. What have we seen regarding pressure drop? We have mentioned that this minus dP by dx is a positive constant. So I can say minus dP by dx is a positive constant, and also it is equal to delta P by L. Pressure drop is represented by delta P. So let me say this entire thing over here is a positive constant. It is a positive constant. So we have over here minus dP by dx is equal to delta P by L equals to a positive constant, where delta P itself is your pressure drop. Fine. Third thing we have seen over here. Third thing is regarding the equation of shear. Third thing we have seen was regarding the equation of shear stress. The equation of shear stress. This shear stress was represented by tau. We saw the equation said tau is equal to minus dP upon dx multiplied to r by 2. Furthermore, we have also mentioned one more equation that said tau naught is equal to minus dP upon dx multiplied to capital R by 2. So these are the equations of shear stress. Tau naught over here represents wall shear stress. It represents wall shear stress. Now let me mention the fourth and fifth terms. The fourth thing over here was regarding friction factor and friction coefficient. Friction factor and friction coefficient. And friction coefficient. We have mentioned that the value of Fanning's friction coefficient F prime is equal to tau naught upon half rho v square. Apart from this, we have mentioned the value of Darcy friction factor F is equal to 4 times F prime. It is equal to 4 times F prime, or you can say it is 4 tau naught upon half rho v square. This is the value. Final term we have seen was regarding Darcy-Weisbach equation. Darcy-Weisbach equation, which gave you the concept of major head loss in internal flow. We have seen that the value of head loss is equal to FLV square by 2GD, or you can say it is equal to 4F prime LV square by 2GD. Both these things are same. So you can Look at these equations. These are the fundamental equations which are required to study any internal flow through pipe. We have also mentioned the criterias. The criterias are steady flow and fully developed flow. Apart from this, let me also tell you one more thing. In some cases, you are not going to have a horizontal pipe. You can have an inclined pipe or vertical pipe. What to do in those cases? How to use these equations or how to manipulate these equations so that they can be useful over there. This is a very, very important point. Please mark it as a note. Very simple concept. If, let me write over here. If a pipe or flow, let us rather use the word flow. If a flow is non-horizontal, non-horizontal. By non-horizontal, I am including both inclined as well as vertical. If a flow is non-horizontal, then what to do? Very simple. Replace every static pressure term by corresponding piezometric pressure. So whenever you see that you are having a flow which is non-horizontal, all you have to do is you remove the static pressure term, P term you remove. So let us say you are having P term, you remove it off. You are not going to use this, remove it off. Then what are you going to use in place of that? You are going to use P star, that is piezometric pressure term. That's it. Then again all the equations are going to be valid. For example, let us say you are having an inclined pipe. Something like this. Don't mind my diagram, it might be rough. Understanding over here is important. If you have a pipe something like this, if you ask me what is the value of tau over here in this case, in general the equation of tau I was having was minus dp upon dx times r by 2. Minus dp upon dx times r by 2. Now this equation is wrong. So how to rectify this equation? To rectify this equation, you have to write minus dp star by dx times r by 2. Now it is going to be correct. Again, this stage, let me also tell you, let me remind you actually, what is x over here? X does not mean horizontal axis. At x again means the axis along the flow. This is x over here. Okay, don't think that you are supposed to check with respect to this axis. That would be totally wrong. You are supposed to again check with respect to the axis along the flow. Fine. So this is a summary of the fundamentals of internal flow through pipes. Let us now start the concept of laminar flow. Till here what we have seen are the fundamentals of internal flow. We are going to use the concepts further in laminar flow also, but let us first of all discuss the basics of laminar flow. Let me write the heading. Laminar flow. Laminar flow. Now how do we define this laminar flow? And where does this word laminar come from? You see, the word laminar is coming from the word lamina. It is coming from the word lamina. And lamina we know means plates. Lamina actually means plates. The meaning of laminar flow is a flow in which plates of fluid or laminas of fluid are sliding over one another with relative motion by the virtue of viscous forces. So let me write over here definition. Let me write the definition over here. A flow in which layers, you can understand these layers, you can understand these layers also as laminas. The flow in which layers of fluid slide over one another, with relative velocities, by the virtue of viscous forces. By the virtue of viscous forces. So what are the important things over here? The important thing over here is layers or laminas of fluid sliding over one another. And why is this happening? It is happening due to the domination of viscous force. Let us do one thing. Let us understand this by taking some physical meaning rather than by taking the fluid mechanics meaning. Let us say, for example, you are having some sheets with high coefficient of friction piled one below the other. Let us say a set of sheets you are having with high coefficient of friction. Let us say sheet 1, sheet 2, sheet 3, so on. You have piled a set of layers or sheets with high coefficient of friction over here. Okay, I'm stressing on the word high coefficient of friction because it is similar to the concept of viscosity in our subject. Let us now say that the first sheet or the upper sheet you are pulling over here. When you start pulling, what happens? If you are pulling this with a velocity capital U, let us say this sheet has moved forward. Now, due to the shear force between the first sheet and the second sheet, the second sheet also is getting pulled parallelly, but it will have a slightly lesser velocity. So let us say it is somewhere over here. Likewise, the next sheet will be somewhere over here. Likewise, the next sheet will be somewhere over here. So you are going to have some relative motion between the adjacent layers. Same things if you apply in the case of fluid, such a flow is known as laminar flow. From here you can get the idea what are the characteristics going to be in the case of laminar flow. First characteristic is already mentioned in the statement over here. It is having domination of viscous forces. If it has domination of viscous forces, tell me, if there is domination of viscous forces, should the Reynolds number value be relatively high or relatively low for laminar flow? for sure the Reynolds number value should be relatively low. And similarly, the kinetic energy also is going to be relatively low. So first point I can mention under characteristics of laminar flow is Reynolds number and kinetic energy of flow. Kinetic energy of flow is relatively low. Is relatively low. This is the first point we are having regarding the concept of laminar flow. Second concept or second point over here. Now tell me, when this is happening in the case of fluids, one layer sliding over the other layer, is there any intermixing of fluid particles from one layer to the other layer? Is there any intermixing of fluid particles taking place? No, there is no intermixing of fluid particles taking place whatsoever. So second point I can mention over here is no intermixing of fluid particles between the layers. So fluid particles are not intermixing between the layers. In simple language, you can say that the laminas over here are maintaining their identity. Whatever fluid particles they started with, later on also the lamina might have moved faster or slower with respect to other laminas, but it is going to end with the same fluid particles. I hope you're following this thing. This is a second point of characteristics in laminar flow. Third point over here. Third point. If there is no intermixing of fluid particles, you are not having any collisions taking place over here. If there is no collision taking place over here and the flow is steady, imagine if the flow is steady and no collisions are taking place, then a fluid particle will maintain its velocity. Its velocity will not randomly fluctuate with respect to time. So I can say no random fluctuation of velocity of fluid particles with respect to time. So fluid particles velocity will not randomly fluctuate with respect to time. Yes, of course, if you increase the discharge, automatically the velocity is going to keep on increasing. Or if you decrease discharge, velocity will decrease. But fluctuation by the virtue of collisions cannot take place over here. Random fluctuations will not take place. This is a very, very important point because you will be seeing exactly opposite of this point happening in turbulent flow. Turbulent flow will be characterized by random fluctuation in velocity, and that will give a different type of shear stress also. Talking about shear stress, let us mention the next point regarding shear stress only. The next point regarding shear stress. In the case of laminar flow, since viscous effects are dominant, the value of shear stress over here is going to be given by mu into du by dy. Mu into du by dy. In other words, you can say Newton's law of viscosity. Newton's law of viscosity is sufficient to calculate shear stress. Is sufficient to calculate shear stress. It is sufficient to calculate shear stress. The reason being, since the viscosity effects are dominant, Newton's law of viscosity is only sufficient. Later you will be seeing in turbulent flow, apart from this Newton's law of viscosity, you will be having an additional viscosity term coming in. And that term is known as eddy viscosity. We'll study in detail that thing later on. Fine. Moving further. Next point over here. The flow has to be rotational. You see, the points are in sequence. Each point is leading towards the next point actually. Once you are having this shear stresses developed, what happens eventually? The fluid element is going to keep on rotating. Therefore, the flow tends to become rotational. Flow is rotational. And let me tell you, this point of flow is rotational was used in one question in IES. Generally, people think laminar flow is a rotational because laminar flow they think is ideal flow. No, laminar flow is a real flow. You have high viscosity effect over here, very much real flow. Yes, not that easily seen flow. Generally, we see turbulent flows. In most cases, our examples are turbulent in nature, but laminar flow still is a real flow and it is a rotational flow as well. One more point over here. Sixth point, let me mention. Surface roughness. Surface roughness of pipe does not affect, doesn't affect losses in laminar flow, losses in laminar flow. So if you are having a rougher pipe or a smoother pipe, laminar flow is going to be unaffected by these kind of surfaces. So it has no effect in the case of laminar. Fine, these are some characteristics of laminar flow. Moving further, let us take some examples of laminar flow now. Examples of laminar flow. Examples of laminar flow. I told you previously also that laminar flow is not that easily seen in practice. In very rare cases you will be seeing this laminar flow. One good example is flow past tiny particles. Okay, for example, you can say dust particles, flow past dust particles and all is going to be laminar flow, right? Flow past dust particles, or you can say from civil engineering point of view, you can say settling of impurities. In environmental, you must have seen this thing, settling of impurities in water. Settling of impurities in water is very similar to flow past dust particles only. These impurities are tiny, very, very small, and flow past these impurities is as good as the first case only. Apart from this, you have capillary flow in soil. Capillary flow in soil. This is also going to be laminar flow. Next thing you can say is, the water rising up in the case of trees. You see, water has to start moving from the roots to the top. That kind of flow is also laminar flow. You can say flow of blood in veins in arteries. Very good example. Flow of blood in veins, laminar flow. You have syringe flow, laminar flow. Many examples are there, but these are not commonly seen examples. For example, you open a tap and you see flow taking place. That is not going to be laminar mostly. It is mostly going to be turbulent in nature. With water, most of the cases you have turbulent flow only. Fine. But there are cases where you have laminar flow which are not general in practice. Next thing, after having seen laminar flow, let us now talk about the critical Reynolds number up till which you can say the flow will be laminar. Fine. I'm going to take three cases over here. First case, flow through pipe. In the case of flow through pipe, we have mentioned this thing already, that in the case of flow through pipe, you will regard the flow to be laminar as long as Reynolds number is less than 2000. Reynolds number is less than 2000. Let me tell you again one more thing, that if the Reynolds number exceeds 2000, in some controlled cases, you can still have laminar flow. For a flow to be laminar, Reynolds number is not that important as the characteristics of laminar flow are important. More important thing is characteristics of laminar flow. If intermixing of fluid particles is not taking place, if random fluctuation in velocity of fluid particles is not taking place, but the Reynolds number has exceeded this value, still the flow can be laminar. Such cases are there, but very rare cases. That is why we will stick to this particular value only. Next thing. Next case we are going to see is flow between parallel plates. Flow between parallel plates. Parallel plates. You are going to see flow between parallel plates will be laminar as long as Reynolds number is less than or equal to 1000, exactly half. Now again half you take. That is going to be the case of open channel flow. In the case of open channel flow, OCF stands for open channel flow, let us say. Excuse me. In the case of OCF, open channel flow, the flow is laminar as long as Reynolds number is less than or equal to 500. One more case which you'll be studying later on in boundary layer also, that is flow past a sphere. Flow past a sphere. Let me write this thing. Flow past sphere. We are going to see this topic in detail in much later topic known as dragon lift chapter. Flow past a sphere, the flow will remain laminar as long as Reynolds number is less than or equal to 1. So these are some standard limits. Remember these limits, very easy to remember. Most of you already remember these two things probably, right? This you will be seeing again. It is also called as Stokes flow. We will be seeing this flow. It is also called as Stokes flow. As a matter of fact, civil people might have seen this kind of flow in settling of impurities. You are having Stokes law valid over there. You might have seen that formula of settling velocity as 1 by 18 mu density of body minus density of fluid into g times d square. This formula you might have seen. This formula actually comes from this concept only. Fine. So this is the fundamentals or the basics of laminar flow. Under this, how many flows are we going to study in our chapter from our examination point of view? So this is very important now. You should know what all things you are going to study beforehand. So we are going to study 3 important types of flow. Okay. Our syllabus in laminar flow is going to deal with 3 things. One is laminar flow through pipes. Laminar flow through pipes. We are going to study this thing. Second thing you are going to study is laminar flow between fixed parallel flat plates. Fixed parallel flat plates. So imagine you are having 2 infinitely big plates parallel to each other. Fine. And both these plates are static condition plates and a laminar flow is taking place between them. Such a flow we are going to study. Next flow is actually graduation of this second point. You are having 2 fixed parallel flat plates. Let us say the plates are relatively moving. Then that flow we are going to study, it is called as Couette flow. Very interesting case. Couette flow. Let me tell you, I find this chapter as one of the easiest chapters in entire fluid mechanics. The reason being, you are having many formula based questions coming from here. Since the questions are formula based, best thing over here is to memorize some important formulas and develop the idea of how to derive formulas very quickly. Because we see many formulas, sometimes you can choke, sometimes you can forget some formulas. So better know derivation of some formulas by remembering primary or basic formulas first of all. So let us conclude the concept of introduction to laminar flow at this. Let us now talk about the equations involved in laminar flow through pipes. We have already seen some fundamental equations of flow through pipes. Now we are concentrating purely on laminar flow, that too through a particular pipe. So let me write the heading first of all. Laminar flow through pipes. Laminar flow through pipes. Now, this topic is one of the simplest topics in entire fluid mechanics. The questions from here are mostly formula based questions. We are going to discuss all the formulas over here, and after discussing the formulas, I will talk to you about how to derive the formulas quickly, even if you know very few formulas. Fine. The first formula we are going to start with over here is the concept of local velocity. It is a concept of local velocity. Now let me tell you first of all that we are going to see three formulas over here regarding velocity alone. The first formula, as I have mentioned, is going to be local velocity. After local velocity, you'll be talking about maximum velocity. Then you'll be talking about something known as average velocity. So three velocities you are going to have. Fine. Now you see, average velocity and maximum velocity are going to be definite formulas which are not variables. But local velocity is supposed to be something which is variable. That means this local velocity is supposed to be a function of some axis. Which axis? I have discussed previously also that we are having two axes along a particular pipe. One axis is the radial axis, the other axis is centroidal axis. Let us say radial axis is represented by small r, centroidal axis by x. Now you tell me, along which axis will local velocity vary? Of course, it should vary along the cross section. That means it is going to vary with respect to r. So I can say over here that once I derive this formula, I am supposed to find that u has to be some function of r. U has to be some function of r. Now let us see the derivation over here. Imagine the cross section of a pipe is something like this. This is the cross section of the pipe. Let us say this over here is my center. The entire radius of the pipe, let us say, entire radius of the pipe, let us say, is equal to capital R. Now what I am doing is, I am choosing the center line, this let us say center line, and I am choosing over here the wall of the pipe. Let us say this is the wall of the pipe. So two things I have chosen over here. This I am calling as center line, and this I am calling as wall of the pipe. I know that the distance from center line till the wall of the pipe is equal to capital R. This distance is equal to capital R. Let us say I choose over here any random point. I am choosing over here any random point. This random point I have chosen is at a distance of small r from center line. It is at a distance of small r from center line. And remember that whenever we talk about the distance from the wall, it is represented by small y. From the wall, always you represent small y. From the center line, you represent small r. Now, I can have a relationship between these three things. What is a relationship? I can say that the value of y is equal to how much? It is equal to capital R minus small r. This is the value of y we are having. Now, I could have chosen this point. This point I have chosen over here. I could choose it anywhere. If I choose it anywhere, the value of small r is going to change, the value of y is going to change, but the value of capital R, it remains a constant. It is remaining a constant. So from here I can imply that, if I differentiate on both the sides, I am going to get over here dy is equal to how much? Now you see d capital R is 0 because capital R is a constant, therefore 0 minus dr. From here I get a very important relationship, and we are going to use this relationship as we go further. The relationship is wherever I see dy, I can very easily replace it by dr over here. So dy is equal to dr. Now why have I done this? Where am I going to use this relationship? We know that the value of shear stress, we have seen this thing, that the value of shear stress tau is equal to minus dp upon dx multiplied to r upon 2. This is an equation we have seen. We also know that this shear stress has to be equal to, in laminar flow, it is purely by the virtue of viscosity, absolute or dynamic viscosity. So I can say it is equal to mu times du by dy. It is equal to mu into du by dy. I hope you have got what I am going to do now. I am going to replace this dy with minus dr. So I can say it is equal to mu into minus of du upon dr. This is the value I am having. Now what I will do is I will write this over here. This is tau, and tau is also equal to minus dp upon dx multiplied to r by 2. This is what I am having. I hope till here what I have written is clear to all of you. Now what I will do is I will cancel off this minus and this minus over here. I will keep only du on one side, rest other terms on the other side. If I do so, what am I going to get? I am going to get over here du is equal to, now you see, dp by dx in the case of a steady flow is going to remain a constant. So please treat this as a constant. 2 is a constant, mu is a constant. So I'm going to get over here 1 upon 2 mu dp upon dx multiplied to r times dr. This is the value of differential u I am going to get. After getting value, what next are we going to do? The most logical thing to do now is integrate. Let us say I integrate over here. The kind of integration I am employing over here is an indefinite integration. Moreover, I hope it is clear to all of you why this has come out. All these things are constant. I am going for indefinite integration. From here, what do I get? I get u is equal to, now r dr integral is r square by 2. If I take the 2 along with this 2, I am supposed to get 1 by 4 mu into dp upon dx multiplied to r square. Now since I have chosen indefinite integration, you are not supposed to forget that there is going to be some constant c coming over here. Now the next aim I'm having is to identify the value of this constant c. To identify the value of constant c, you would require some boundary conditions. Think logically. What is a boundary condition for a real flow you are going to have? Always think that when a real flow is there, one boundary condition should be at the wall. We know at the wall, by the virtue of no slip condition, the velocity has to be equal to 0. So I can say over here that at the wall, I can say over here, at the wall of pipe, at the wall of pipe, by the virtue of no slip condition, what do we know? We know that the value of radius is equal to capital R and the value of velocity has to be equal to 0. This is the boundary condition we are going to employ in the above equation. So let me do one thing. Let me save this as some equation 1. I am saving it as equation 1. So if I put these boundary conditions, let us say this is my boundary condition. So now what I'm doing is I'm putting in boundary conditions in equation 1. What do I get if I put in these boundary conditions in equation 1? I would get over here 0 is equal to 1 by 4 mu into dp upon dx multiplied to capital R square plus c. This is what I get. From here I can say that the value of c, from here I can say that the value of c is equal to how much? The value of c would be this entire term over here, before c, whatever entire term you are having, with a negative sign. Now mind you, I was waiting for a negative sign to appear so that I can give that negative sign to dp by dx. So now I can write over here, it is 1 by 4 mu minus dp upon dx times capital R square. This is the value I'm having. I've got the value of this constant c. So let me save this value of c. Now what I'm going to do, I'm going to rewrite this equation 1 over here. So equation 1, how will it change? Equation 1 becomes u is equal to, let me start with c first of all. Please be with me. I am writing c first of all. The value of c is equal to 1 by 4 mu times minus dp upon dx times capital R square. I have just written the value of c now. I am supposed to write this value now. Now, be careful. This value I am going to write with minus times minus. You see, minus times minus is again plus. So I know that this entire value is plus. So I can say minus into minus. So let us say minus into 1 by 4 mu into minus dp upon dx times small r square. Now you see, minus times minus is again plus. So this is my value for equation 1. So let me do one thing. Let me simplify it in some form. It is easy for me to understand. So I can now say that this value of u has now become equal to 1 by 4 mu common to minus dp upon dx common to capital R square minus small r square. This is the equation of velocity we have. This is the equation of velocity we have in the case of laminar flow through pipes. This is the equation of velocity we are having in the case of laminar flow through pipes. So let me mention over here, this is the equation of local velocity in laminar flow through pipes. In laminar flow through pipes. This is the equation of local velocity we are having. Now regarding this local velocity, what all things can we conclude? The first thing I can mention about over here is u is a function of r. U is a function of r. Before deriving this equation itself, we were hoping to get u as a function of r, and that we have got over here. U has become a function of r over here. Moreover, how is u varying with respect to r is the next question. So now the second thing I have to talk about over here is how is u varying with respect to r. I can say that first thing, it is not linear, it is parabolic. What is indicating that it is parabolic? Look at the power of r over here. It is square. So I can say u varies parabolically with respect to r. Next, is it increasing with r or decreasing with r? Look at this sign over here in front of r. The sign is negative, which implies that u is decreasing parabolically with respect to r. So I can say that local velocity decreases parabolically with respect to r. So local velocity decreases parabolically with respect to r. Two are important over here. First thing, u is not increasing, it is rather decreasing. So it is decreasing. How is it decreasing? It is decreasing parabolically with respect to r. Last thing, tell me what should the value of r be in order for me to get maximum local velocity? That is very logical. If you see, there is one way of maximizing, that is going mathematically and all those things. I'm not interested in that now. I want you to think logically and tell me, if I make this value of r equal to 0, then what happens? Automatically, I'm going to get my u maximum. So I can say from here, one moment please. One moment. Yes, I can say from here that maximum local velocity is attained at center line. In other words, when small r is equal to how much? 0. So these are some notes, some theoretical points I can mention regarding the concept of local velocity in the case of laminar flow through pipes. Now what I am going to draw is a very important curve, or it is a very important representation, and that is the velocity profile of velocity in the case of laminar flow. Let us see how the velocity profile is going to be. Imagine that this is certain pipe you are having. This is a pipe you are having. Let us say this is a center line, excuse me. This is the center line you are having. We know that this axis over here is r axis. This axis is r axis. Furthermore, let us say I look for the velocity profile at a particular section. The velocity profile at a particular section. At the center, I'm supposed to have the maximum. So I have over here maximum local velocity, let us say. Maximum local velocity. I'm supposed to have some kind of parabola here. Some kind of parabolic curve. It is supposed to be symmetric. So this is how the velocity profile is going to be in the case of laminar flow through pipes. Laminar flow through pipes, and this happens to be my U maximum. Let me represent it as U maximum. This is how the velocity profile is. You can say that this is parabolic in nature. Parabolic in nature. Many simple examinations ask these kind of questions repeatedly. Fine. After having drawn this thing, let us move further. Let's talk about how much is the value of maximum velocity. Now for maximum velocity, I have to put the value of r equal to 0. So I can say over here, U maximum is actually U itself, but at r equal to how much? 0. U maximum is local velocity itself, but at r equal to 0. So I can write from here, it is equal to, the value of U was 1 by 4 mu into minus dp upon dx multiplied to capital R square minus small r square, put in the value of small r equal to 0. So from here I get the value of U maximum. How much is the value of U maximum? U maximum is equal to 1 by 4 mu minus dp upon dx multiplied to capital R square. This is the equation for maximum velocity or center line velocity. So you can say this is center line velocity in laminar flow through pipes. Laminar flow through pipes, let us say. This is a center line velocity. Now what I will do is, I know that this is an equation of U. I am going to write this U again. I am going to write U again. U I know is equal to 1 by 4 mu minus dp upon dx times r square minus r square. This is what we know. I can rewrite this as 1 by 4 mu minus dp upon dx multiplied to r square. I am taking r square common from here. Mind, from here I am taking r square common. What am I left with now? I am left with 1 minus r square upon capital R square. I am left with this thing. Now I want you to observe, what is this value equal to? What is this value equal to? It is equal to U max. So from here I can write that. The value of U is equal to U maximum multiplied to 1 minus R square upon capital R square. This is one more way you can represent the value of U in the case of laminar flow through pipes. So there are three equations I have mentioned over here. Let me summarize those equations once. So in your summary of the formulas, there are three equations you are going to write down under local velocity. The first thing you have seen is the formula of u as 1 by 4 mu minus dp upon dx times capital R square minus small r square. This is a formula. See, actually, if you remember only this formula, it is sufficient. You can do anything else. But still, let us say, second thing we have to remember over here is the value of u maximum. What are you going to do for getting u maximum? All you are going to do is, you are going to make this r square equal to 0. If you make r square equal to 0, you get u maximum. So the value of u maximum is equal to 1 by 4 mu minus dp upon dx times capital R square. This is u maximum. Third formula or third relationship, what is it talking about? Talking about the ratio of u to u maximum. The ratio u to u maximum, just now we have seen it was equal to 1 minus r square upon capital R square. So these things are talking about the concept of velocity, local velocity in the case of laminar flow through pipes. After having seen the concept of local velocity, the next thing we are going to look at are two formulas. First one is regarding the formula of discharge. Second one is regarding the formula of average velocity. Mind you, average velocity is one of the most important formulas in entire topic. Let us start discharge now. So second formula, let us say discharge formula. Discharge represented by Q. Now you see, the problem with this discharge now is, in general you would say discharge is equal to area into average velocity. But now we do not have the value of average velocity, we have the value of local velocity. So what do we do now? In this case, we have to talk about differential discharge, and from differential discharge you have to develop complete discharge by integration. Let us say the cross section of the pipe is something like this. It is having a radius capital R, as I have mentioned previously also. Let us say I take a differential area over here. I am choosing a differential area. This differential area is at a distance of small r from the center, and let us say it is having a thickness equal to dr. This is having a thickness equal to dr. Let us say a very tiny strip we are having, very thin strip. Now the question first of all is, how much is this differential area equal to? This differential area is equal to how much? It should be equal to 2 pi r times dr. So I can write over here, it is equal to 2 pi r times dr. 2 pi r times dr. This is a value of differential area we are having. Now I can say that the value of differential discharge, is equal to local velocity times differential area. I have the formula for differential area established already. Now recall the formula for u. The formula for u is equal to u maximum multiplied to 1 minus small r square upon capital R square. We know this thing. Let us do one thing. Let us take this capital R square outside. So the value of u would be equal to u maximum upon capital R square multiplied to capital R square minus small r square. This is a value of local velocity u you are having. Now from here I can say the value of differential discharge is equal to, put in the value of u over here, so you are having u maximum upon capital R square multiplied to capital R square minus small r square multiplied to differential area, that is 2 pi r times dr. Now next thing, if I want to calculate the value of discharge, I have to integrate this thing. I have to integrate this. So let us say the value of q is equal to integral of this thing. For writing integral, let me take the constant terms aside. The first thing I'm having constant is 2 pi. 2 pi is a constant. Then I have u max, a constant, upon capital R square, a constant, multiplied to, let us say, r square into r minus r cube whole common to dr. This is the variable. So let us now integrate this, where r is ranging from 0 till r is ranging till capital R. This is the value. Now from here I can say, I am continuing over here, the value of q is equal to 2 pi u maximum upon capital R square into, what is the integral of r square into r dr? It is going to be r square into r square by 2 minus r cube dr integral is going to be equal to r power 4 by 4. It is ranging from 0, r equal to 0, till r equal to capital R. Now let me tell you, if I put in over here r equal to 0, I am going to get 0 for this entire thing. If I put r equal to capital R, I am going to get over here, q is equal to 2 pi u maximum upon capital R square into r square into r square by 2 is going to be equal to r power 4 by 2 minus r power 4 by 4. R power 4 by 2 minus r power 4 by 4 is again going to be r power 4 by 4. So the value of q is equal to 2 pi u maximum upon r square into r power 4 by 4. This is the value. Now what I am going to do is, I am going to write this in a particular format. I am going to write this in a particular format which is suitable for me later on. That format is q is equal to, look over here, I can cancel off a 2 from here. I am remaining with a 2. I can cancel off r square. I am remaining with r square. So I have over here pi r square multiplied to u maximum by 2. So this is the value of q. This, though it is not used commonly as a formula, but let me save it as some equation. Let us say we have seen already two equations, or for this set, let us say this is some equation number 1. Let me save it as some equation number 1. Fine. Now recall that the value of u maximum is equal to, let me write over here, q is equal to pi r square multiplied to, recall u maximum, it was equal to 1 by 4 mu into minus dp upon dx multiplied to capital R square whole divided by 2. From here ultimately you are going to get the equation of q. The equation of q therefore is going to be equal to how much? Pi by 8 mu. So I have chosen this pi, I have taken 4 mu and 2, pi by 4 mu minus dp upon dx times r power 4. This is the equation of discharge. So you can say this is discharge in laminar flow through pipes, in laminar flow through pipes. This is the equation of discharge in laminar flow through pipes. Now after getting this, immediately after getting this, what I'm going to do is I'm going to find out the value of average velocity. For finding average velocity, what I'll do is I will choose this value, excuse me, I'll choose this particular formula now. Let us say we are now speaking about average velocity. Average velocity. This average velocity is v. I can say that the value of v has to be equal to, the value of v has to be equal to q upon area, is it not? By continuity equation we can say v is equal to q upon area. I already have q over here. If I take this as the value of q, then I'm having v is equal to, in place of q I can write pi r square into u maximum by 2, this is the value of q, and area we know is equal to pi r square. So in this case I can cancel off pi r square with pi r square. So now the value of v becomes equal to, v becomes equal to u maximum upon 2. This is the formula for average velocity. This is the formula for average velocity in laminar flow through pipes. If you want, you can further put in the value of u max and get the formula for average velocity as v is equal to, if you recall, u max was 1 by 4 mu, this is going to be 1 by 8 mu. Rest everything for u max and v remains same, minus dp by dx multiplied to capital R square. These are the values of average velocity. Now I would want you to remember only this thing. Don't even remember the equation of discharge. Let us say you do not even remember the equation of discharge. From all this you have seen, just remember throughout this slide whatever you have seen, just remember one thing. and that is, you're supposed to remember that average velocity is equal to u maximum by 2. And one more thing I would want you to remember, which actually you can't forget, that is q is equal to area times average velocity. If you just remember these two things, automatically you'll get the value of v. For example, let us say this is what you remember. From here, what would you get? From here you would get that the value of v is equal to how much? U max by 2 means what? 1 by 8 mu and rest of it minus dp by dx multiplied to r square. And from here what would you get? From here you would get pi r square into average velocity is this thing, that is 1 by 8 mu minus dp by dx multiplied to r square. That is why I am not stressing more over remembering all the formulas. I am stressing only over remembering some basic formulas. Over here in this slide, you are supposed to remember these two formulas. Eventually, you would get those formulas. Anyway, excuse me. After having seen this, let me take a very simple standard question whose answer, if you remember, it is better for you. And that question comes commonly in some basic examinations in IES and SSC, JEE and all those things. The question is, at what value of small r upon capital R, the local velocity is equal to average velocity in laminar flow through pipes. You can understand the rest of it in laminar flow through pipes. This is the question, let us say. Very simple question. Answer, it is better if you remember. Local velocity is equal to average velocity. So basically u is equal to v. It is given to you. What is the formula for u and v from common point of view? I can say u is equal to u maximum multiplied to 1 minus r by r whole square. This is the value of u. And what is the value of v? V is equal to u maximum upon 2. From here what I can do is, I can cancel off u max and u max. So what do I have now? I have from here 1 minus r by r whole square is equal to half. This is equal to half, which implies that r upon r whole square is equal to 1 minus half, that is again equal to half. So the value of r upon r over here is equal to 1 by root 2. R by r is equal to 1 by root 2. This basically means, even though we have got the answer, what does it basically mean? It means that at small r equal to root 2 of capital R, or excuse me, I'm sorry, I'm mistaken over here. At small r equal to capital R by root 2 or 0.707 times capital R, the local velocity the local velocity is equal to average velocity, is equal to average velocity. The local velocity is equal to average velocity. So this is regarding the concept of discharge and average velocity in the case of laminar flow through pipes. Now at this point, I would encourage you to do a small exercise, okay? And that is, this might be slightly difficult, let me tell you. That is regarding finding the values of, find the values of alpha and beta. Alpha and beta. What is alpha? Alpha is kinetic energy correction factor and beta is momentum flux correction factor for laminar flow through pipes. For laminar flow through pipes. Flow through pipes. Find the value of alpha and beta in the case of laminar flow through pipes. Even though you don't find it, you have to remember the values. I hope you remember them. But if you do this exercise, you will become more familiar with the kind of questions those might appear in examination. And let me tell you, this is not a simple question. This is going to be slightly difficult from mathematics point of view, but it is still doable. You are supposed to get the value of alpha as 2 and the value of beta as 1.333 and so on. That is basically 4 by 3. After having seen the equation of velocity and discharge, let us create a problem. This problem is going to be slightly difficult, but a very good one. Let us say you have a particular pipe. Imagine there's a pipe over here. Suppose the radius of this pipe is equal to capital R. The radius is equal to capital R. Let us say the flow through pipe, the flow through pipe is perfectly laminar, fully developed laminar flow, let us say. Laminar flow. Fine, this is given to us. Now the question is saying, find the ratio of discharge in the region R equal to 0 to R equal to capital R by 2 to the discharge in rest of the pipe. Now this is a very good question. The question is saying, find the ratio of discharge in the region Q is equal to R equal to 0 to R equal to capital R by 2. That basically means, let us say within this pipe, I am choosing a central portion over here. Let us say this central portion over here has a radius capital R by 2. So suppose this portion over here is my region 1. So in this region, what is the value of discharge? Versus the discharge in the rest of the pipe. So what is the discharge in this region versus the discharge in the rest of the pipe? Let us say we call this as Q1 and the rest portion as discharge Q2. This value is equal to how much? This is the question. Now at this point of time, I would want you to pause the video and imagine how to approach this question. The question is in front of you. Pause the video for yourself and imagine how to approach the question. Let us see now how to solve this thing. Let me save it over here. Now one idea of solving the question would be something like this. Imagining that the value of Q1 is equal to the discharge by taking a portion of r by 2 as radius. Okay, recall what is the formula of discharge? The formula for discharge was pi by 8 mu into minus dp upon dx multiplied to r power 4. R power 4 over here would be r by 2 power 4. Now some of you probably have thought of this idea, taking the value of discharge Q1 like this and the value of discharge Q2 equal to discharge in the entire pipe would be equal to how much? Pi by 8 mu into minus dp upon dx multiplied to r power 4, this is the discharge in the entire pipe, minus Q1. Now if you have thought of this idea, let me tell you, you have mistaken. This point over here is wrong. It is wrong. This cannot be correct. Now why is it wrong and when is it going to be correct? Please understand the equation of discharge Q is an equation which is derived for some standard limits. You see, if I'm having a pipe over here, imagine that there's a particular pipe. Suppose I have a pipe something like this. In this pipe, if I have a parabolic velocity profile starting from 0 at the boundaries, attaining a maximum at the center, only then I can apply the formula of discharge Q as pi by 8 mu minus dp upon dx multiplied to the corresponding radius power 4, whatever is the radius of this pipe. Okay, only then I can apply. But the problem is, if you look at the portion of Q1, it is going to have a velocity profile, let us say from here till here. This is the portion of velocity profile for Q1. Let us say Q1 is having this portion of velocity profile. Now mind you, this velocity, the boundary velocity for Q1 is not starting at velocity equal to 0. Fine. That is why I cannot apply this formula directly. Then what am I supposed to do for approaching this question? For approaching this question, I have to go for the first principle method. That is, taking the local velocity, finding out differential discharge, and then integrating by using the corresponding limits. Only then will I get the value of discharge Q1. Let us see how to approach this thing. I hope it is clear to you what mistake is present over here. Let us start now how to approach the question. I am going to start with the pipe again. Let us say this is a pipe's cross section I am having. I am taking a differential area. Let us say this is some differential area. This is some differential area. Differential area, let us say. This ring region is having a radius small r and it is having a thickness equal to dr. Having a thickness equal to dr. Let us say the differential area of this portion, is equal to 2 pi r times dr. And we also know that the value of local velocity is equal to how much? The value of local velocity is equal to u maximum upon capital R square multiplied to capital R square minus small r square. This was the value of u local velocity we have seen. Now I can say at this point that the value of discharge dq, which is equal to local velocity times differential area, is equal to how much? It is equal to u maximum upon capital R square multiplied to capital R square minus small r square multiplied to 2 pi r times dr. This is the value of differential discharge. Now I can say the value of q1 is equal to integral of differential discharge, where the radius is ranging from r equal to 0 till r equal to capital R by 2. Therefore, it has to be equal to, now let us see what all terms are going to remain constant. I see 2 pi is constant, u maximum can be taken outside, upon r square is taken outside, integral of r square into r minus r cube times dr ranging from r equal to 0 till r equal to capital R by 2. Now if you integrate this, how much would the value of q1 come out to be equal to? The value of q1 over here would be equal to 2 pi u maximum upon r square times the integral of r square into r dr is r square into r square by 2, fine, minus integral of r cube dr is r power 4 by 4, ranging from limits 0 till capital R by 2. Now if I put the limits 0, the entire value would become 0, therefore lower limit is as good as nothing over here. We have to only concentrate on the upper limit. So I can say this value is equal to 2 pi u maximum upon r square times, now look at this, r square into, now you see if I put in this value it is going to become r square by 4, and then you are having a 2 over here, it ultimately becomes r power 4 upon 8 minus. Now you see if I put in r by 2 over here, I am going to get r power 4 divided by 16. 16 times 4 is 64. So I am having r power 4 upon 64. This is the value of q1. Now you see it ultimately becomes q1 equals to 2 pi u maximum upon r square times. Now you see LCM is going to be 64, so 8 in the numerator, 8 minus 1 is 7, so it is 7 r power 4 divided by 64, which is equal to, let me save this value now, which is implying, let us say, which is implying that the value of q1 is equal to 2 cancels with 64, r square cancels with r power 4 over here, r square remains. So I am having pi by 32 into 7 u maximum times r square. This is the value I'm having. Fine. This is the value of q1. Now, what is the value of q2? Let me save this first of all. Let me save this value as certain equation number 1. Now, the question is, what is the value of q2? What is the value of q2? We know that the value of q2 has to be q in the entire pipe minus q1. And we know that q in the entire pipe is equal to pi r square multiplied to average velocity. Average velocity we know is equal to u maximum by 2. This is the value of q. So basically this value is this much. And minus q1, we just now have calculated the value of q1. The value of q1 I'm going to borrow from here. So I have over here 7 pi r square by 32 times u maximum. Now again, if you look at the LCM is going to be 32. That means I'm supposed to multiply and divide by 16 over here. So the value of q2 now becomes equal to 16 pi r square u maximum by 32 minus 7 pi r square u maximum by 32. If you calculate this value of q2, it comes out to be equal to how much? 9 pi r square u maximum by 32. This would be the value of q2. Let me save this as equation number 2, let us say. Now, we need to get the value of q1 upon q2. We need to get the value of q1 upon q2. I can say the value of q1 upon q2 is equal to how much? q1 was equal to 7 pi r square u maximum by 32 and q2 is equal to 9 pi r square u maximum by 32. If you calculate this thing, this ratio, very simple value, q1 upon q2 is going to be equal to 7 by 9 or equal to 0.777 and so on. This is the answer to the question asked. 7 by 9. Similarly, if I would ask you what is the ratio of average velocity in region 1 to average velocity in region 2, then what would you do? Try that by yourself. All you have to do is you have to divide q1 upon a1, similarly q2 upon a2, then you would get the value. Now that we have seen the equations of velocity and discharge, let us go for the next formulas. The formulas from here on will be having very small derivations. The first one we are going to see is the equation of pressure drop, very important equation, and this equation is also known as Hagen-Poiseuille equation. So let me write over here the fourth equation which we are going to have is pressure drop. This equation is pressure drop equation, and this pressure drop equation is sometimes referred to as Hagen-Poiseuille equation. Pauli equation. Let us see how to identify the equation of pressure drop. The key over here, the key over here is only one point. If you understand that, it is sufficient. And that point we have discussed already. It says that wherever you see minus dp upon dx, you can replace it with delta p by length. This is the point you have to understand. So minus dp by dx is equal to delta p by l. The reason I'm again repeating over here, that the pressure drop is going to be linear. Are you following? So pressure is going to linearly decreasing along the length. If it is decreasing linearly along the length, then the ratio of pressure drop per unit length throughout is going to remain the same. That is why you can replace minus dp by dx with delta p by L, where delta p stands for drop in pressure. Now, how to use this idea? Recall the formulas for average velocity and discharge. We know that the value of average velocity is equal to 1 by 8 mu minus dp by dx was there. What I will do is, in place of minus dp by dx, I will be writing delta p by L multiplied to r square, multiplied to r square. If I write velocity average in this form, then I can imply from here, that the value of delta p would be equal to how much? Delta p would be equal to 8 mu and L would shift over here, r square in the denominator. So I'd be having over here 8 mu VL upon r square. This would be the value. Now let us say I want to replace r with diameter. Then this is going to become d square by 4. 4 goes on top. Therefore, I would be having over here the equation something like this, that the value of delta p, is equal to 32 mu VL upon d power 4. This would be the equation of delta p. This would be the equation of delta p from velocity point of view. Let me save it as some equation number 1 over here. Now, if I recall the formula for discharge, Q was equal to how much? Recall, it was equal to pi upon 8 mu. Again, minus dp by dx was there, which I am replacing by delta p by L times r power 4. Again, if I only look for delta p from here, what am I going to get? I am going to get that the value of delta p is equal to, how much is it going to be? 8 mu QL, 8 mu QL upon pi, and r power 4 would be in the denominator. So pi r power 4 over here. This would be the value. Again, if I write this in terms of diameter, I'm going to have put in place of r d by 2. So d by 2 whole power 4 is going to be d power 4 by 16. 16 goes to the numerator, then I would be getting the value of delta p as 128 mu QL upon pi times d power 4. This would be the value of delta p in that case. Let us say this is equation number 2. Now both these equations are sometimes referred to as Hagen-Poiseuille equations also. Again, I do not stress much on remembering this thing. If you do not remember this, if you are not able to remember this, it's still fine. All you have to remember over here is that wherever you see minus dp by dx, you can replace it with delta p by L. It's a matter of 2 steps. You would get the formula anyway. But for that, you have to remember some basic formulas like velocity or discharge formula. Either formula is fine, or at least u maximum formula along with the relationship of average velocity and u max. That also is fine. Let us move further. After having this drop in pressure, our next aim is to identify the value of head loss. So let us say fifth formula we are looking at over here is the value of head loss. It is the value of head loss. Now for finding the value of head loss, the criteria is you have to go back to Bernoulli equation, and you can say from Bernoulli equation that, or we have already seen this thing if you recall, that for a horizontal pipe we have found out that the value of head loss was supposed to be equal to delta P upon gamma. If the pipe was having uniform cross section and the datum level everywhere were same, velocity head and datum head would anyway cancel off on either side. So only pressure difference would contribute towards head loss. If you remember only this much, then you can say that the value of head loss is equal to, now if you remember the value of delta P just now we have seen, so from there I can say the value of head loss is equal to 32 mu VL by D square. This is the value of delta P. All I have to do is put a gamma over here. I would get the value of head loss. Similarly, we have seen 128 mu QL by pi d power 4. This is the value of delta P. All I have to do is I have to put a gamma over here, gamma pi d power 4. Now this is going to be the equation of head loss. This is going to be the equation of head loss. After having seen the equation of head loss, next thing is we are going to look at the value of power loss. Sometimes you see we have to deal with power loss also. So let us say fifth we have seen just now. So let us say sixth point over here is equation of power loss. Equation of power loss. Let us say this is represented by P with a subscript L over here. Now remember, when we discussed the concept of Bernoulli equation, over there we have mentioned that power is having a particular formula in our subject. What formula is it? We know that the value of power has to be equal to gamma into Q into head. Now since I want power loss over here, what head am I going to choose over here? I am going to choose head loss over here. So the value of power loss is going to be gamma times Q times head loss. Now if it is so, then I can say, you see over here, this is the value of head loss. Let us say I multiply by Q and by gamma over here. Then what would happen? This Q would square up and gamma would vanish off, is it not? Then the equation we are going to have, for the value of power loss is going to be equal to how much? 128 mu Q would square up, so Q square times L upon gamma is vanishing off, so I have over here pi times d power 4. This would be the value of power loss. Again, I do not stress much on remembering this formula, but this you have to remember for sure. If you remember that, you can easily get these things. You see, getting the refined most formula is a matter of 2-3 steps, but for that you have to remember the fundamental formulas first. Next, after having seen the value of power loss, we are now going to shift towards the concept of friction. If you recall, we have discussed about two types of factors. One is known as friction coefficient, other is known as friction factor. Let us start with the friction coefficient. Let us start with friction coefficient. So this is formula number 7 in our list. Friction coefficient in the case of fully developed flow through pipe is also known as Fanning's friction coefficient. So we are now looking at Fanning's friction coefficient. Friction coefficient. Fanning's friction coefficient. I am going to represent this Fanning's friction coefficient with F with a prime over here. F dash also you can say. This is Fanning's friction coefficient for me. Now, how to develop the equation of Fanning's friction coefficient? Recall, the fundamental formula for a friction coefficient is friction coefficient F prime is going to be equal to the ratio of wall shear stress to dynamic pressure. So let us say tau naught to dynamic pressure, that is half rho V square. This ratio is known as friction coefficient. In the case of flow through pipe, it has a specific name known as Fanning's friction coefficient. Now what I am going to do is, I am going to recall the formula for tau naught. The formula for tau naught is equal to minus dP upon dx multiplied to minus dP upon dx multiplied to capital R by 2, minus dP by dx multiplied to capital R by 2. And the formula for average velocity is equal to 1 by 8 mu minus dP upon dx multiplied to R square. This is a formula for average velocity we are having. Now what I will do is, I am going to say this is also equal to tau naught upon half rho. I'll say V square is equal to V times V. I hope it is fine. There's no harm in writing V square as V times V. Now what we will do is, in place of tau naught, we'll put this value. In place of tau naught, we'll put this value. In place of one velocity, we will put this value. And other velocity, we will leave as it is. I hope you're following what I'm going to do in the next step. So now I can say that the value of f prime is equal to in case of tau naught, I am supposed to write minus dP upon dx times R by 2 R by 5 upon half rho. In place of one velocity, we'll put the refined formula for velocity, which is 1 by 8 mu into minus dP upon dx times R square. Do not forget one more velocity is there. Write it as it is. The other velocity as it is. Now it is time for simplification. Look over here. I can cancel this minus dP by dx and minus dP by dx. I can cancel 1r with 1r over here and half with half over here. Fine. After having cancelled all these things, I would be getting over here, this value is equal to 8 mu would go on top. 8 mu is on top upon rho VR, rho V, this would be the value. I can also write this as 16 mu upon rho VD. I believe there is no problem in writing this. Okay, 8 mu by rho VR is 16 mu by rho VD. Now, please concentrate at this. What is this mu upon rho VD representing? Mu upon rho VD is representing 1 by Reynolds number. Since it is equal to 1 by Reynolds number, I can say from here that the value of f prime is equal to 16 upon Reynolds number. This is the formula for Fanning's friction coefficient. This is the formula for Fanning's friction coefficient. Fanning's coefficient of friction. In the case of laminar flow. Now, the next formula, immediate next formula we are going to look at is going to be Darcy friction factor. So let us say formula number 8 in the sequence. Formula number 8 in this sequence, very important formula, which is known as Darcy friction factor. Darcy friction factor. This Darcy friction factor is represented by F. It is represented by F, and the value of F is equal to 4 times F prime. It is equal to 4 times F prime. This is the formula for Darcy friction factor. All I have to do is multiply this value with 4. So I can say from here that the value of F is equal to 4 times F prime. Just now we have seen is 16 upon Reynolds number. 4 times 16 is going to give you 64. Therefore, the value of F is equal to 64 upon RE. This is the formula for Darcy friction factor. Some books just mention this as Darcy friction factor as 4F prime itself. They do not use F, they rather use 4F prime. So 4F prime or F is equal to 64 upon Reynolds number. These are the formulas required in the case of laminar flow through pipes. Let me quickly summarize what are the formulas, or the sequence is important. The summary, let us say over here. Summary of the formulas. What are the various formulas involved? The first formula over here is going to be regarding the concept of local velocity. Local velocity. The second formula and third formula over here are going to be what we have derived were discharge and then average velocity. Now what I want you to do is I want you to change the sequence for remembering purpose. Don't go for discharge and average velocity. Think like this: average velocity and discharge. Average velocity and discharge. Why so? The reason is, if you know the formula for average velocity, getting discharge is just area into average velocity. Fine. So derivation sequence is different, memorization purpose sequence is different. You see, when you find out the value of local velocity, over there you are going to come across u as a function of r, and also you will find u in terms of Umax also, from where you will get, let us say, the value of U maximum. You will know the value of average velocity. You will know the value of average velocity V as U maximum by 2. And then you would know the value of discharge as area into average velocity. This, let us say, is the first set of formulas we have. Now comes the second set of formulas. The second set of formulas, let us say, fourth, fifth, and sixth. These are the second set of formulas. First one over here is drop in pressure. Second one over here is head loss. Third one over here is power loss. Now all these formulas are having some basic primary formulas. If you remember, then you can easily derive them in examination also. So what do we have over here? Let us say for drop in pressure, what do you have to remember? For drop in pressure, all you have to remember is wherever you see minus dP upon dx, replace it by delta P by L. For head loss, all you have to remember is the value of head loss is equal to delta P by gamma. The value of power loss is equal to, it is equal to gamma into Q times head loss. Let us see, this is the second set of formulas. The final set of formulas is very, very easy formulas. Most of you, I hope, remember it by now. The final set of formulas, let us say, seventh and eighth formula. Both these formulas are quite easy. This first one is coefficient of friction, which, let us not go for the fundamental formula now. Straight away, since it's an easy formula, memorize it over here itself. It is 16 upon Re. And the value of Darcy friction factor, which is 4F prime or given by F, it is equal to 64 by Re. Let us say this is the final set of formulas. So three set of formulas you are having over here. The formulas, you see, might be in plenty, but it is quite easy to memorize these formulas. One more thing, and very important thing, probably the most important thing at this stage. Please understand, whatever derivations we have done over here are corresponding to a pipe which is horizontal. So we are discussing only about a horizontal pipe which is experiencing laminar flow. It is very much possible that the pipe might be inclined. So let us say it is possible that the pipe is inclined. So what to do if you are having an inclined pipe? Imagine there is an inclined pipe over here which is experiencing laminar flow. This pipe is experiencing laminar flow. In this case, how will the formulas change? What do I have to keep in mind whenever this happens? Very simple. All you have to understand is an inclined pipe is equivalent to a horizontal pipe. It is equivalent to horizontal pipe. An inclined pipe is equivalent to horizontal pipe, only with one difference. What difference is it? The difference is inclined pipe is equal to horizontal pipe with pressure replaced by piezometric pressure. Pressure is replaced by piezometric pressure. That means wherever you see P, you are going to replace it by P star. Let us take an example. We know that the formula for shear stress, let us say the formula for shear stress, in general, was equal to minus dp upon dx times r by 2. This is the formula for shear stress we know of. But now the moment the pipe is inclined, you are going to use a formula which is for horizontal pipe with only one difference, and that difference is you are going to say minus dp star by dx. Mind you, x axis is still the centroidal axis, minus dp star by dx multiplied to r by 2. So wherever you see static pressure, replace it by piezometric pressure. Again, all your formulas are going to be valid. That's the only thing you have to keep in mind when you see pipes which are inclined. After having seen laminar flow through pipes, let us now start the next concept in laminar flow, and this is laminar flow between two fixed parallel plates. Very simple concept and very similar to what you have seen in the case of flow through pipes. This is laminar flow between two fixed parallel plates. Fixed parallel plates. We are going to follow the same sequence what we have seen in the case of flow through pipes. Let us first of all start with deriving the differential equation which governs the flow over here. For that purpose, suppose I choose a plate over here. Let us say this is one plate I am having. There is another plate parallel to this. Let us say this other plate which is parallel. Suppose the distance between both these plates is equal to capital B. The distance between these plates is capital B, and let us say the centroidal axis over here is this axis. This is the centroidal axis. Now my next aim is to identify which are the axes based on which various parameters are changing. I see there are two axes. One is along the flow and the other is perpendicular to the flow. So I have over here, let us say, an axis in this direction and I have an axis along the flow. This along the flow axis is known as x-axis and this I am choosing as y-axis. So these are two axes I am having. Next thing, I am supposed to choose elementary fluid element, let us say, on which I am going to apply continuity, Bernoulli and momentum equation to develop the equation. Let us say the differential fluid element I am choosing is somewhere over here. This is a differential fluid element. Let us say I have chosen differential fluid element. Something like this. This is an element I am choosing. Let us say this element is present at a distance of y from the wall of the pipe, and this element is having its own height equal to dy. The height of this element is equal to dy, and let us say the length of this element is equal to dx. The length of the element is equal to dx. Suppose I choose this as section 1 and I choose this as section 2. I can say by continuity equation, the value of A1 into V1 has to be equal to A2 times V2. Now please observe over here. The value of A1 over here is dy multiplied to the width. A2 is equal to dy again multiplied to the width. Now the width is same, so therefore happens A1 and A2 both of them have to be equal, which further implies that the value of V1 over here is equal to V2. So I can say this, let us say, is my equation 1 I am having. The velocities are same. Now what we're doing is I'm going to write, or I'm going to draw the control volume along with the forces acting on this element. Now please observe. If I take this fluid element, let us say I take a bigger picture of this fluid element. Suppose this is the element I'm having. What are the various forces acting over here? First force acting is the pressure force over here. Let us say there is some pressure force over here, and that is equal to P times. How much is the area it is acting over here? It is acting over an area of dy times width. Let us say width is equal to W. Width perpendicular is equal to W. The pressure at this particular section, lateral section, let us say, is equal to P plus dP whole times area. What is the area again? It is again equal to dy times width. So let us say dy times width is the area. Fine, the pressure forces are done with. Now please observe, if I take a fluid element below over here, is it going to move faster or slower? For sure that fluid element is closer to the wall, therefore it has to move slower. If it is moving slower, it is going to apply a shearing stress in the backward direction. It is applying a shearing stress in the backward direction. And let us say this shearing stress is equal to tau. It is equal to tau, and it is multiplied to the shearing area. The shearing area over here has to be dx multiplied to W. So dx multiplied to W, let us say. Now talk about the fluid element present over here. Closer to the center, higher velocity, moving faster, therefore it is trying to shear our subject element in the forward direction. So let us say I have over here tau plus d tau multiplied to area. Area is equal to dx times W. Dx times W. So I have all the forces acting over here established in x-axis. Now let me write the equation. Let me write the equation over here. Summation of force in x-axis has to be equal to delta m dot times velocity in x-axis. I know that this is also equal to m dot into v2 minus v1. Sometime back I have already established v2 and v1 are same, therefore this value becomes equal to 0. From here I can imply that the value of net force acting in x has to be equal to 0. It has to be equal to 0. Now the question is, what is the net force equal to? You can look at this diagram. Let us look at the forces now. I'm starting first of all with pressure force. I'm taking this direction over here as a positive direction. If I start with the pressure force, I'm having over here P times dy into width, minus P plus dP times dy into width, Next, I'm having this positive plus tau plus d tau times dx into width, minus tau times dx into width has to be equal to 0. Please observe the equation once. Pause the video if you have any difficulty in understanding the equation. Very simple equation. Let us now cancel off dW everywhere and put pressure terms on one side and shear terms on the other side. So what have we got from here? From here we can say that first of all P times dyW and P times dyW cancel off. W anyway is cancelling off everywhere. So I have minus dP times dy, and over here let us say tau and tau cancel off, is equal to minus d tau times dx. This is what we got. Again minus and minus cancel off. If minus and minus cancel off, I have over here dp upon dx is equal to d tau upon dy. This is the equation we have got. This is the governing equation. So I can say equation governing the flow. This is the equation governing the flow. Once I have got this equation, what am I going to do next? To understand the equation of velocity, let us say I want to develop equation of velocity now. Equation of velocity. This is my aim right now. I want to develop the equation of velocity. To develop the equation of velocity, I can say that the value of tau has to be equal to mu into du upon dy. If tau is equal to du of mu into du by dy, let us put this value of tau over here. This implies that the value of dp upon dx has to be equal to mu into d2u by dy2. This is the value I'm going to have. So mu into d2 upon dy2 is the value of dp upon dx. Let us integrate this. I can say by integration, what do we get by integration over here? The value of u has to be equal to 1 by 2 mu times dp upon dx multiplied to y square plus some constant c1 times y plus another constant c2 over here. This is the equation I'm having. 1 by 2 mu dp upon dx times y square plus c1 times y c2. My next aim will be to identify the value of c1 and c2. I can straight away identify the value of c2. So if I put the boundary condition that y equal to 0, how much should the value of u be equal to? Recall, y equal to 0 basically means you are at the wall, at the fixed end. At the fixed end, by no slip condition, we know the velocity over there has to be equal to 0. So let us say by boundary conditions, I can say at y equal to 0, the value of u is also equal to 0, and this is no slip condition. This is by the virtue of no slip condition. So put in u equal to 0, y equal to 0. This straight away implies that the value of c2 also should be equal to 0. You are having 0 here, 0 this entire thing, so c2 automatically becomes 0. So now my equation of velocity u has come down to 1 by 2 mu times dp upon dx times y square plus c1 times y. How do I get the value of c1? Think over it. How do I get the value of c1 over here? Imagine the velocity profile. Where do you expect the velocity in this case to be maximum? The velocity is going to attain its maxima at the center. At the center, I know that. y has to be equal to b by 2. Fine. At the center, y is equal to b by 2. Velocity has become maximum. So the velocity u has become maximum. What next? If the velocity is maximum, immediately you can say that the value of du upon dy has to be equal to 0. I got one more boundary condition now. So I can say at y equal to b by 2, du by dy has to be equal to 0. Let us see what this is giving me. First of all, develop the value of du by dy. The value of du by dy has to be equal to, now look at this thing, very simple, differentiate with respect to y. So I have 1 by 2 mu dp upon dx times 2y plus c1. I can cancel this 2 and this 2, which implies du upon dy has to be equal to 1 by mu dp upon dx times y plus c1. Now what is the boundary condition we are having? Let us say I am putting this boundary condition over here. If I put this boundary condition over here, then I'm going to have du by dy is 0. 0 is equal to 1 by mu into dp upon dx times, in place of y I am going to put b by 2. Let us say I put the 2 over here, b by 2 plus c1. From here you can get the value of c1. So you can say the value of c1 is equal to 1 by 2 mu minus dp upon dx multiplied to b. This is the value of c1 over here. Now you see I was getting a minus, but I chose to club that minus with dp by dx. I chose to put that minus with dp by dx because we know that dp by dx is actually a negative quantity. We have discussed this thing in the case of flow through pipes also. dp by dx is negative and minus dp by dx has to be positive. Therefore, this is what we have. Now what we have to do is use this value of c1 in the equation of velocity. I'm going to use this value of c1 in the equation of velocity. If you have forgotten the equation, just now we have seen the equation was u is equal to 1 by 2 mu times dp upon dx times y square plus c1 into y, that is 1 by 2 mu times minus dp upon dx into b multiplied y. This is the equation we are having. Let me arrange this equation in a format which is more suitable for me. The equation now I can say is u is equal to, I am taking 1 by 2 mu minus dp upon dx common. Take the last term first. What are you remaining with? You are remaining with b times y, and take this term later on. So you are remaining over here with minus y square. This is the equation of velocity in the case of laminar flow between fixed parallel flat plates. 1 by 2 mu minus dp by dx times by minus y square. If you see over here, how is the velocity varying? Is it a linear variation with y or parabolic? Of course, it is parabolic variation. So from here you can write down that velocity u varies parabolically with respect to with respect to y-axis. The variation is parabolic with respect to y-axis. You should vary parabolically with respect to y-axis. Now you see, I am not writing whether it is increasing or decreasing. The reason is there is going to be a portion of increase and there is going to be a portion of decrease over here. How so? Please, if you look at the velocity profile, important thing, velocity profile over here, let us say these two plates are parallel. Imagine them to be parallel if you're not seeing them parallel. The distance between these two lines or these two plates is equal to capital B. Let us say this is a certain centroidal axis. If I look at the velocity profile at any section, I'm going to have a D, parabolic velocity profile. Y is starting from here. X is in this direction. Now, initially the velocity is going to increase parabolically. Then it attains maxima. A mirror image is going to be developed over here. So you're going to have a parabolic variation, something like this. This is maximum. Likewise, you're going to have symmetry. Imagine symmetry if my diagram is not looking that way. Please imagine the symmetry. So this is how the velocity is going to vary with respect to y-axis. Now immediately let me now look at the value of u max. This is my u maximum. My next immediate question over here should be, what is the value of u maximum? So let me write over here maximum velocity. Maximum velocity is equal to how much? How much is the value of maximum velocity? To identify the value of maximum velocity, I have to take a condition that this u maximum is basically equal to local velocity at y equal to b by 2. Local velocity at y equal to b by 2. So let us say u maximum is equal to, local velocity formula is 1 by 2 mu minus dp upon dx into b times y. In place of y, I am going to put b by 2 minus y square. Y square means b square upon 4. This is the value I am having. If you simplify this thing, you are going to get the value of u maximum is equal to 1 by 2 mu into minus dp upon dx times, you see over here, b square by 2 minus b square by 4 should give you b square by 4. B square by 4. Therefore, the value of u maximum velocity is equal to, take this 4 over here, you have 1 by 8 mu times minus dp upon dx times b square. This is the value of maximum local velocity or centerline velocity in the case of laminar flow between two fixed parallel plates. So till here you have seen two velocities. One velocity was local velocity and the other velocity is the maximum of that local velocity. Next, what I'm going to do is I'm going to look for the value of average velocity, and the value of average velocity I can get provided I know the value of discharge. So what I will do is I will look at the value of discharge. So let us say, next thing, I am looking over here at the value of discharge. How much is the value of discharge in the case of laminar flow between two fixed parallel plates? Now you see, My local velocity is keeping on varying. If my local velocity keeps on varying, then what I will do is I will first calculate the value of differential discharge. I can say differential discharge has to be equal to local velocity multiplied to differential area. So let us say the local velocity was equal to how much? 1 by 2 mu minus dp upon dx multiplied to b times y minus y square. This is what I'm having. Look over here, u has become purely a function of y. That means my differential area should have dy over here. So what I'll do, let me look at the picture again. Let us say these are the two fixed plates I'm having, two fixed plates. At any random y location, I have given you the value of u. I will assume that this u is functioning for a small thickness over here. U is functioning for a small thickness over here. And how much is that thickness equal to? Let us say thickness is equal to dy. So what is the area going to be equal to? The area is dy multiplied to the width perpendicular to your screen, and that width, let us say, is w. So I can say this area is equal to, let us say, differential area over here. How much is that area equal to? So 1 by 2 mu minus dp upon dx multiplied to b times y minus y square. Area is equal to how much? Dy multiplied to the width perpendicular. If I want the complete value of discharge, I would have to integrate this thing. So let us say q is equal to integral of this thing. Take all the constant terms aside. 1 by 2 mu is constant, minus dp upon dx is a positive constant, w constant again. I am having b times y minus y square into dy going into the integral. Let us say this is going into the integral. Where is y ranging from? Y is starting from 0, ending till where? Capital B. So I can say y is equal to 0 till y is equal to capital B. This is the integral. Very simple integration. So what do we have over here? Q is equal to how much? Q is equal to 1 by 2 mu minus dp upon dx times w multiplied to. Please answer me. by dy integral should give you how much? by square by 2. So by square by 2 minus cube dy integral should give you y cube by 3. Y cube by 3 ranging from where to where? Y is equal to 0 till y is equal to capital V. Put in the values. If I put in the value y equal to 0, I'd get a 0 over here. If I put the value y equal to b, I would be getting q is equal to 1 by 2 mu minus dp by dx multiplied to w multiplied to b cube by 2 minus b cube by 3. What b cube by 2 minus b cube by 3? It is b cube by 6. Take that 6 over here. So you are having the value of q is equal to 1 by 12 mu minus dp upon dx multiplied to b cube times w, where w is the width perpendicular to the screen. This is the value of discharge we have. This is the value of discharge. Let me write over here. Now what was purpose initially of finding the value of discharge? We were supposed to find out the average velocity. So let us move to average velocity now. Once you know the value of discharge, average velocity is a very simple thing. Average velocity, I'm going to represent by capital V. And how do we get the value of average velocity V? We know V has to be equal to Q upon area. V is equal to Q upon area. So that is equal to 1 by 12 mu minus dP upon dx times B cube into W divided by area over here is equal to how much? I'm not going to draw the diagram now. This time you have to imagine, please. The distance between the plates was equal to capital B, and the distance coming perpendicular to your screen is equal to W. So it is equal to B times W. So I can cancel off this W. I can cancel off one B over here. I'm remaining with B square. From here, I get the formula. I get the formula for average velocity as 1 by 12 mu into minus dP upon dx multiplied to B square. This is the value of average velocity. This is the value of average velocity. Average velocity. I do not want you to remember this equation actually. In the summary, I'm going to tell you again how to memorize these formulas. But at this stage, it is better to recall the value of maximum velocity. The value of maximum velocity was 1 by 8 mu, and rest of everything is same. It was 1 by 8 mu, rest everything was same. So let us do one thing at this stage. Let us try to establish a relationship between average velocity and maximum velocity, and that is very important. So let us say the value of V upon U maximum is equal to how much? It is going to be equal to 1 by 12 mu times minus dP by dx times B square for average upon 1 by 8 mu times minus dP by dx times B square for maximum. So therefore the value of average velocity to maximum velocity would be equal to 8 by 12, which is equal to 2 by 3. This is more important than remembering this equation. This is a more important relationship. So till here in this particular slide, you have seen how to find out the local velocity, the maximum velocity, and average velocity along with discharge, or relationship of average velocity and U maximum. After having seen the equations of velocities, let us move further now to pressure drop. Pressure drop. Now this pressure drop is represented as delta P. What we have discussed in the case of flow through pipes still applies over here. We have discussed that wherever you see minus dP upon dx, you can replace it by delta P upon L. So recall the formula you had for average velocity. The formula for average velocity was equal to 1 by 12 mu minus dP by dx. In place of minus dP by dx, I put delta P by L times B square. This is the value of velocity. From here I can say that this implies that the value of delta P has to be equal to how much? 12 mu VL, 12 mu VL upon B square. Similarly, if you look at the formula of discharge, Q is equal to 1 by 12 mu minus dP by dx is delta P by L multiplied to B cube times W. From here I can say that the value of delta P has to be equal to 12 mu QL upon B cube times W. These are the two formulas we can have for delta P. Now it is not more important to remember these formulas, but still I'm highlighting this. What is more important is to remember this relationship, basic relationship. And the reason for this relationship to be valid is pressure decreases linearly along the length of the flow. Now this is regarding the concept of pressure drop. The immediate effect of pressure drop is head loss. The immediate effect is head loss. So let us say next thing we have is head loss. Head loss. How to calculate the value of head loss? You can go for Bernoulli equation. The Bernoulli equation says, imagine you are having a flow taking place in a horizontal system. Let us say section 1, section 2 over here. I am not drawing the entire picture of two parallel plates. I am drawing a line diagram over here. Section 1, section 2, both of them are in the same datum, horizontal system we are having. I can write over here the value of P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2 plus head loss. This is what we can write over here. The cross section area is same, the velocities at section 1 and section 2 are same, can cancel them off. Since I'm having a horizontal system, Z1 equal to Z2, I can cancel them also off. So what am I left with over here? I'm left with the value of head loss is equal to P1 minus P2 upon gamma. In other words, it is equal to delta P by gamma. If head loss is equal to delta P by gamma, from delta P we know that delta P we know is equal to 12 mu VL by B square. I can say now gamma times B square will give me head loss. Similarly, there is one more equation for head loss, 12 mu QL upon gamma times B cube into W. This should give you the value of head. Immediately after looking at loss, you can now derive the formula for power that is lost. So let us say thing is power loss. How to develop the equation of power loss? Long back when we discussed the concept of Bernoulli equation, we have mentioned that the value has to be equal to gamma times Q times head. I want to loss, therefore I will choose over here head loss. So let us say in the equation you multiply gamma and Q. What is going to happen? Gamma and gamma will cancel off. Q will become squared up. So now the equation of power loss the equation of power loss becomes equal to 12 mu q square into L upon B cube into W. This would be the value of power loss. This would be the value of power loss. Now the final formula, again an important formula, very important formula. It is regarding the concept of shear stress. This is the final formula in the case of what do you call flow between parallel plates. The formula is for shear stress. Shear stress. How to develop the equation of shear stress? We know that the value of shear stress tau has to be equal to mu into du upon dy. It has to be equal to mu into du by dy. So therefore I can say tau has to be equal to mu into d by dy of, what is the value of velocity? We have seen already velocity was equal to 1 by 2 mu minus dp upon dx multiplied to b times y minus y square. If I calculate this thing, I'm going to have tau is equal to mu into 1 by 2 mu comes out as constant minus dp upon dx also comes out as constant multiplied to b minus 2y. I can cancel mu and mu over here. What happens if I cancel mu and mu? I'm going to get the equation of tau as minus dp upon dx multiplied to b minus 2y whole divided by 2. This is the equation of tau I have. This is the equation of tau we are having. So let me mark this as an important equation for shear stress. Now recall, when we were discussing the concept of shear stress in flow through pipes, we have also mentioned a statement over there, that is, how is it varying with respect to radial axis, in this case with respect to y. I see that it is going to vary linearly with respect to y. So I can say tau varies linearly with respect to y. Tau varies linearly with respect to y. So remember these things, linearly with respect to y. Furthermore, there is a particular shear stress which is all the more important for us, and that is wall shear stress. And we know at wall y is equal to 0. So immediately what we can do is, we can say at the wall of the pipe, at the wall of, not the pipe in this case, at the wall of the flow, let us say flow, we know that the value of y is equal to 0 and the shear stress is represented by tau naught. Therefore, if I wish to calculate the value of tau naught has to be equal to how much? It has to be equal to minus dp upon dx multiplied to, put in y equal to 0, all you have is b by 2. This is the value of your maximum shear stress or wall or boundary shear stress. So let me name this as wall or boundary shear stress. Wall or boundary shear stress. After looking at this, now what we are going to do is we are going to draw the shear stress profile in the case of laminar flow between plates. If you observe the shear stress profile, let's say you have two plates parallel and fixed, and let us say this is a center line you have. At any section you wish to draw the shear stress, we know at the center the shear stress has to be 0, linearly vary to attain maximum at the wall. There should be symmetry. This is how you are going to have the shear stress. Mind you, you are measuring y. You are measuring y not from the center. You are rather measuring y from the wall, any of the walls. So let us say this is your y-axis and the corresponding shear stress over here. So this is regarding the formulas involved in the case of laminar flow between two fixed parallel plates. Let us now summarize all formulas we have seen in the case of laminar flow between plates. Let us see what are the formulas we have seen. I'm going to stress over here on what you have to remember, and you can sometimes skip formulas. Those formulas also I'll mention over here. The first formula which you are bound to remember, there is no way you can escape that formula. That is regarding the value of u. U is equal to how much? U is equal to 1 by 2 mu into minus dp upon dx multiplied to b times y minus y square. You are bound to remember this formula. If you remember this formula, you will eventually be able to get the value of u maximum. So let us say whatever I write in white ink is something which you are bound to remember. You can't escape that. Whatever I write in the other yellow ink, let us say, that you will easily be able to derive in examination. Okay, if you don't remember that, still you can manage off. You can say the value of u max is equal to u at y equal to b by 2. Therefore, you will get the value of u max quite easily as 1 by 8 mu minus dp upon dx times b square. This is the value of u max. Next formula which you are supposed to remember, which you can't escape, that is the formula of v. We have to know that the value of v is equal to 2/3 of u max. V is equal to 2/3 of u max. If you know that v is equal to 2/3 of u max, you will easily be able to write v is equal to 1 by 12 mu minus dp upon dx times b square. Now you see only two things still here. You are supposed to remember. You can get all these things. Next thing is all the more simple, and that is regarding discharge. What are you going to remember for discharge? You can say Q is equal to area times velocity is more than sufficient to remember the value of discharge. Okay, Q is equal to area times velocity for discharge. So from here you can say that the value of Q, the value of Q has to be equal to 1 by 12 mu into minus dp upon dx multiplied to b cube times w. In many of the cases what happens is they will say the value of width perpendicular is equal to 1 unit. If they say width is equal to 1 unit, you can just say the value of Q is equal to B cube. So this is also a very standard formula. Stopping at B cube is a standard formula provided the width perpendicular is equal to 1 unit. If width is involved, please mention width, no problem at all. Next thing, the fourth thing over here is regarding the value of delta P. For delta P, you have to remember minus dp upon dx is equal to delta P by L From here you will get that the value of delta P is equal to 12 mu VL by B square. If you are having width involved, then W you can mention over here. Otherwise, you can just mention B square also. Likewise, you can say it is equal to 12 mu QL upon B cube. Fine. This is delta P. Next thing you are having is regarding the value of head loss. For head loss, what you are supposed to remember is head loss is equal to delta P divided by gamma. Head loss is delta P by gamma. Therefore, what happens? The value of head loss now becomes equal to 12 mu VL by gamma times B square, or equal to 12 mu QL by gamma times B cube. Next formula is for power loss. So let us say sixth formula is for power loss. What are you going to remember for power loss? Gamma into Q into head loss. This is sufficient. So eventually you will get the value of power loss as 12 mu Q square L upon B cube. This is the value of power loss. The final formula, which is for shear stress, you have to remember the formula. The formula for shear stress is equal to minus dP upon dx multiplied to B minus 2y upon 2. This is the value. If you want wall shear stress, then you can say the value of y is equal to 0. Therefore, minus dP upon dx multiplied to B by 2. Now, if you observe over here, the formulas you are supposed to remember are very few and very simple formulas. The first formula you have to remember is for velocity. That is a formula, proper formula. Rest of them are just relationships. You see over here, V is equal to 2/3 U max, a relationship. Q is equal to AV. If you want also, you can't forget this now. Minus dP by dx is delta P by L, a relationship. Head loss is delta P by gamma, a relationship. This again is a very fundamental equation. And this of course is a formula you have to remember. Now very few formulas. At this moment, let me also tell you what to do if you are having inclined flow system. Let us say you are having two plates which are not in the horizontal setup. They are in the inclined setup, okay, and still they are fixed plates. Again, the same logic what you have used in the case of flow through pipes. As a matter of fact, wherever you see a flow is non-horizontal, always do the same thing. Replace any pressure term by corresponding P star. For example, the value of head loss will no more be equal to delta P by gamma. It becomes delta P star by gamma. The value of tau will not be equal to minus dP by dx times whatever. It will be equal to minus dP star by dx. Mind you, again, x over here is the axis of flow. X is not the horizontal axis, x is the axis of flow. I hope this clears the concept of flow between two fixed parallel plates. We are going to extend this topic further by taking slight complication, and that is known as Couette flow later on. Till now we have seen two types of flow under laminar flow concept. The first one was laminar flow through pipes. Second one was laminar flow between two fixed parallel plates. The flow we are going to look now is an extension to laminar flow between plates, and this flow is known as Couette flow. It is known as Couette flow. A very interesting case, and quite a simple case if you apply simple logic. This Couette flow has appeared in examination recently for 2 marks in GATE examination, and before that it was not that much common. Let us see how to understand the concept of Couette flow. Recall the case of laminar flow between two fixed parallel plates. Imagine you are having two plates, both of them are fixed. Both the plates are fixed, and there was a laminar flow taking place between them. Then you know that by the virtue of no slip condition, the velocity of both the walls was equal to 0, and then the velocity profile was parabolic in nature, something like this. Now what we are going to do is, we are going to extend this flow, but we are going to make one of the plates moving. Imagine that this fixed plate previously, this fixed plate is now given some velocity such that it is able to move. How will the flow then look like? Let us see. So let us say a plate which was previously fixed is given a certain velocity. Let me represent by capital U, and another plate is kept fixed. Another plate is kept fixed. If you look at the velocity profile, applying the same logic of no slip condition, I can say that over here the velocity profile or velocity has to be equal to 0 by no slip condition, and over here by no slip condition the velocity has to be equal to capital U. So let us say velocity is capital U. Now what is happening? I am supposed to again draw a parabola over there, but this time the parabola is not going to be perfectly symmetric. It is rather starting from capital U and ending at 0. Let us say you are having something like this. This kind of flow is known as Couette flow. This kind of flow is known as Couette flow. And I can define the Couette flow now as laminar flow between two parallel plates such that one plate is moving relative to the other. One plate is moving relative to the other. So a laminar flow in which you are having one plate moving to the other is known as squid flow. Now, to understand different types of squid flow, I am going to look back at this particular case. Flow between two fixed parallel plates. In the case of two fixed parallels, if I take this axis as x-axis, I was having over here the value of dP upon dx as negative. That means the pressure was decreasing as I move forward. Let me tell you, this is the most important thing to understand the concept of squid flow now. Everything in squid flow depends on the value of dP upon dx. In other words, how is the pressure going to vary along the length flow is going to determine what kind of squid flow I'm having. Now let us see the various types of squid flow. So let me write over here types of squid flow. Types of squid flow. Types of squid flow. Now imagine that you are having a plate over here, a plate which is moving, and the other plate that is fixed. The other plate that is fixed. Let us say the moving plate over here is having a certain velocity capital U. And in this particular case, if I take this axis over here as x-axis, and this entire distance over here between the two plates, if I take as capital B, I am taking the distance between the two plates as capital B, and the axis perpendicular over here as y-axis. Let us say this is my axis. Fine. If I create a condition wherein the value of dP upon dx is equal to 0, the value of dP upon dx is equal to 0, means that the pressure everywhere is going to remain same in x-axis. Then what will happen? How will the velocity profile over here look like? Let us say I take a section over here. I know that at this particular point, by the virtue of no slip condition, the velocity has to be equal to 0. Let me take this point as point A. The velocity at point A has to be equal to 0. If I take this point as certain point B, the velocity at point B has to be equal to, by no slip condition, capital U. Let us say this is capital U. Now tell me, if the value of dP upon dx is equal to 0, what do you expect the velocity profile to look? dP by dx equal to 0 basically says that the flow which was taking place by the virtue of pressure difference, which was creating a parabolic kind of velocity profile, is not happening. Now the flow is taking place purely due to the motion of this plate. Are you following? Let me repeat it now. The flow which was taking place due to pressure difference between two sections, which was creating parabolic velocity profile, is not taking place right now. The flow is purely taking place by the virtue of the pulling of this particular plate. This means that my velocity profile should be the simplest velocity profile, no parabolic nature, rather it should be a linear velocity profile. I am supposed to have something like this, a linear velocity profile. So now let us say the velocities over here are something like this. The velocities are something like this. This kind of quit flow is known as simple quit flow, or it is also called as pure quit flow, also called as plain quit flow. Three names are there. You are having simple or pure or plain quit flow. Any of these names is correct. So in the case of simple quit flow, most important or characteristic equation is the value of dp upon dx is supposed to be equal to 0. At this moment, I want you to imagine what is going to be the velocity profile of simple quit flow. For sure, if I say that the velocity u is the velocity present here, I can say this u has to be a function of y-axis. It should vary with respect to y-axis. Function basically means dependency. As y keeps on changing, the value of u also is changing. This is the simplest change because it is a linear change. I can look at these two triangles. Look at a smaller triangle over here. This triangle and the bigger triangle. These two triangles, if you see, you will find both these triangles to be similar. So I can say the value of this u, small u, upon capital Y has to be equal to complete velocity capital U upon complete distance capital B. So from here I can say that the value of u upon y, this velocity, let us say this velocity upon the corresponding height, has to be equal to complete velocity, that is capital U, upon complete height over here is equal to capital U. In other words, in the case of simple quit flow, the value of u has to be equal to capital U multiplied to y by b. Let me save this equation. This is the value of velocity in the case of simple quit flow. Now, after considering the simple quit flow, let us understand the various types of quit flow now. There are two more types of quit flow we are having. Let us take the next case. Before I give you the net result, I want you to imagine something. Let us say you are having a laminar flow taking place between two fixed parallel plates. So imagine something like this. You are having two fixed parallel plates. There is a laminar flow. There is a laminar flow taking place over here. Laminar flow taking place over here. So what would happen? You would have a velocity profile something like this. You would have a velocity profile something like this. To develop this kind of velocity profile, the required condition is the value of dp upon dx is supposed to be equal to negative. If the value of dp upon dx is negative, I am going to get this type of velocity profile. Now to this, I am going to add one more flow. The flow I am adding over here is a simple quit flow. Let us say you have a simple quit flow over here. Same distance between the two plates. The plate is moving in the forward direction. Simple quit flow implies that the velocity has to be having such a profile so that this is also equal to capital U. Let us say both these things I am combining now. If I combine both these things, I am going to get one type of quit flow over here. How will this look like? Imagine how will this velocity profile look like? How will the velocity profile over here look like? This is going to have a parabolic result. You see, a linear plus parabolic has to be again equal to parabolic. But now the boundary conditions are going to slightly change. If you take a section over here, we know that the velocity at this point has to be equal to 0, and we know that the velocity at the topmost point has to be equal to capital U, has to be equal to capital U. And now I'm going to have a parabolic curve starting from capital U to 0. So let us say something like this. This is again going to be a parabola. This is again parabolic in nature. This kind of quid flow I'm calling as a forward quid flow. I'm calling this quid flow as forward quid flow. So I can say the condition required for attaining a forward quid flow is when the value of dp upon dx in the flow is negative. So in this particular case, let me write over here, the value of dp upon dx is negative, less than 0. That is when you are going to get a forward quid flow. So how can I write down the the idea of forward quid flow in a simple language? I can say that a forward quid flow is quid flow in which the laminar flow is taking place in the same direction. It is taking place in the same direction as the plate is moving. Quid flow in which the laminar flow between the plates takes place in the same direction, or in the direction in which moving plate moves, or moving plate is moving, in which the moving plate is given the velocity. Now if you see over here, the laminar flow and the plate which is moving, both of them are having same direction. That is when I'm going to have forward quid flow, and the mathematical condition for that is the value of dp by dx has to be negative. Now I'm going to take the opposite case of this thing. It's going to be backward quid flow. Let us see how the backward quid flow is going to look like. Imagine over here that you are having a laminar flow taking place between two fixed plates. A laminar flow is taking place between two fixed plates, but in this direction. Let us say something like this. So if I take this as my x-axis, I can say over here the value of dp upon dx has to be positive. If dp by dx is positive, it means that the net head in this case is increasing in the right hand side direction, therefore the flow should take place in the opposite direction. So I'm having dp by dx positive. Let us say to this I am adding a simple quid flow. To this I'm adding a simple quid flow. A simple quid flow would look something like this. If the velocity over here is capital U, its velocity over here also is going to be capital U. Now I want to see the net result, which is going to be my backward quid flow. How will the result look like? Let us say I have the moving plate over here. I have the fixed plate over here. I have the fixed plate over here. Now, if I take a particular section, if I take a particular section, then by the virtue of motion with a velocity capital U over here, at this point I'm supposed to have capital U velocity, at this point I'm supposed to have zero velocity. Now I'm supposed to draw a parabola, but mind you, my parabola is not in the forward direction, my parabola is in the backward direction. So now the velocity profile would look something like this. This would be the velocity profile in this case. This kind of quick flow I'm going to call as backward quick flow. It is called as backward quick flow. And what is the condition, mathematical condition required for backward quick flow? I have highlighted over here. The condition is the value of dp upon dx has to be greater than 0. That is when we're going to have backward quick flow. If you want to write down this in a statement, then you can say that laminar flow is in the direction opposite to the motion of moving plate, opposite to the motion of moving plate. Such a flow is going to be backward quick flow. So till here you have understood the types of quick flow, and let me remind you, all you should remember mathematically for types of quick flow is the condition which is given by dp by dx. If dp by dx is 0, you are having simple quick flow. If dp by dx is negative, you are having a forward quick flow. If dp by dx is positive, you are having backward quick flow. Let us now talk about the velocity in quick flow. So let me mention over here, velocity in quick flow. This is from where you can expect questions coming in. And this is a very simple case, very simple case. To understand the velocity in quick flow, I am not going to do any derivation. I will very simply prove the velocity. Recall that the velocity profile in quick flow was a combination of two velocity profiles. One was simple quick flow velocity profile, and other was the corresponding laminar flow between the two plates. Just now we have done that, right? If the velocity profile is a combination of two velocity profiles, I can also say that the velocity equation should be a combination of two velocity profiles. So now at this stage, let me tell you, if I look for the velocity in quick flow, I can say it is equal to velocity in simple quick flow, plus the velocity in laminar flow between fixed plates. If you remember this thing, it is very easy to develop the equation of velocity. So let us do one thing. Let me draw a case of quick flow over here, which is representing all the three cases. Let us say two plates. The distance between the two plates I know is capital B. This distance is equal to capital B. This axis over here is y-axis, and the forward axis over here is x-axis. I have three types of quick flow. I'm going to represent all of them together. Let us say I take a section over here. Let us say this plate is moving with certain velocity, capital U. The velocity of this plate is equal to 0. Velocity over there is equal to 0. I can have three types of flow. This happens to be the first one. That is a simple quick flow. The second one, let us say, is a forward quick flow. Something like this. Forward quick flow. The third one, let us say, is a backward quick flow. Backward quick flow. Let us say this is a first case, this is a second case, and this over here is a third case I'm having. All of them are going to have over here velocity u equal to capital U, and over here it is equal to 0. So this is a diagram you're having. I hope you follow the diagram. I'm combining all the three cases in a single case. Now let us satisfy this equation. I can say that the local velocity is equal to capital U. How much should this be equal to? How much should this velocity be equal to? It should be a combination of velocity of simple quick flow. Recall, what is the velocity in the case of simple quick flow? Velocity in the case of simple quick flow is capital U multiplied to y upon b. We have done this thing some time back. Not difficult at all. Capital U into y by b plus. What is the velocity of laminar flow between two fixed parallel plates? This is something we have derived also. It was 1 by 2 mu into minus dp upon dx multiplied to b times y minus y square. This is going to be the net equation of velocity in the case of quick flow. This is going to be the equation of velocity in the case of quick flow. I can also rearrange. This is sufficient to remember. So let me highlight this thing. Please remember this equation. I can also rearrange this in a particular format which might be easy to remember. Let us see what is the format we can rearrange this in. Now look over here. I am going to write this equation as u is equal to capital U into y by b, capital U into y by b plus 1 by 2 mu into minus dp upon dx minus dp dx. Now I have to write b times y minus y square. Instead of writing b times y minus y square, let us take b square common over here. If I take b square common, let us say I'm taking b square common over here. What will I have? I'll have over here y by b minus y square upon b square. Y square upon b square. This can be an equation. You see, I'm having everything now in terms of y by b. So this is one more way of writing the equation of velocity in the case of quick flow. So you are having two equations over there. Both of them are the same equations. I would prefer you to remember the first one, that is an easier equation. The second one also is an equation which is preferred sometimes because everything is having y by b format over there. Anyway, this is regarding the concept of velocity in quick flow. From here you can find out the velocity for every type of quick flow. Not only forward or backward or simple, every quick flow can be taken care over here. Again, let me remind you that the most important term happens to be this dp upon dx or minus dp upon dx term. This term is the most important term that is going to decide how will the velocity look like. Fine, after having seen the velocity profile, next thing we are going to do is we are going to look at the discharge concept in the case of quick flow. Let us see the discharge. So let me mention over here discharge. For discharge, again we have to use the same logic. Discharge in quick flow is going to be a combination of discharge in simple quick flow plus discharge in laminar flow taking place between two plates. So let us do one thing. Let us first of all develop the equation of discharge in simple quick flow. So let us say, what is the value of discharge in simple quick flow equal to? What should be this value? Let us see now. Look at the velocity profile. I'm not going to draw a very neat diagram for you now. You have seen the diagram multiple times. The velocity profile is something like this. Velocity profile is something like this. This entire distance is equal to capital B. This is equal to capital U. Let us say the width perpendicular to the board coming out or perpendicular to your screen coming out is equal to capital W. Capital W is the width perpendicular. The plates should have certain width, right? That width is capital W. Now I can say the value of discharge over here is equal to area of this triangle multiplied to the width. So this Q of simple quick flow has to be equal to area of the triangle. Area of triangle is half base times height. Therefore, half base is equal to capital U, height is capital B. Now, area of triangle multiplied to the width. Therefore, multiplied to W. This is the equation of discharge in simple quick flow. Now, let us write the equation of discharge for complete quick flow. So from here I can say that discharge in quick flow has to be equal to discharge in simple quick flow plus discharge in laminar flow. Now I'm not writing entire thing. I hope you follow this thing. Laminar flow between fixed parallel plates. Fixed parallel plates. So therefore the equation now comes Q is equal to, first of all this part, that is half capital U into B multiplied to W plus. Recall the form of discharge in the case of laminar flow between two fixed parallel plates. The form over there was 1 by 12 mu minus dp upon dx multiplied to b cube times w. B cube times w. This is going to be the equation of discharge. This is going to be the equation of discharge. Now if you see, I can also write this equation of discharge as, let us say I take B times W common. If I take B times W common, I am left over here with half of capital U plus 1 by 12 mu minus dp upon dx multiplied to b square. Now observe over here, what is this B times W representing? B is the height between the two plates, W is the width perpendicular. This is basically the cross section area. This is basically the cross section area. Now let us say I transpose this cross section area to left hand side. So what will happen? I'll get Q upon cross section area. I'll get now Q upon cross section area. So let us say Q upon B times W is basically discharge upon cross section area, and we know that discharge upon cross section area is average velocity. So I can say the average velocity of quick flow has to be equal to the remaining part, that is capital U upon 2 plus 1 by 12 mu minus dP upon dx times B square. So this is the formula for average velocity. This is the formula for average velocity in quick flow. Average velocity in quick flow. So till now we have defined three things. One is the equation of local velocity, one is the equation of discharge, one is the equation of average velocity. What is the next thing we are going to do? The last thing we are going to do is to develop the equation of shear stress. So let us say I'm looking for the equation of shear stress. So let me mention over here shear stress now. Shear stress. How to develop the equation of shear stress? Again, I'm going to say the value of shear stress in the case of quick flow is a combination of shear stress in simple quick flow plus shear stress in laminar flow between two fixed parallel plates. For that reason, I have to first find out how much is the shear stress in simple quick flow. So my first aim over here is tau in simple quick flow is equal to how much? For that purpose, recall what is the velocity profile in simple quick flow or velocity equation. I know the velocity equation is capital U into y upon b. This is the equation of velocity we are having. If this is the equation of velocity, I can say the value of du upon dy is a constant which is capital U upon b. From here, I can say tau in simple quick flow has to be equal to mu times du upon dy. That is equal to, or it implies, tau in simple quick flow is equal to mu into capital U upon b. Capital U upon b. Let me highlight this thing. This is the shear stress in simple quick flow. Now what I'm going to do is I'm going to add two equations. I'm going to say over here that the value of tau in quick flow is equal to tau in simple quick flow plus tau in laminar flow between plates, parallel plates. So therefore, the value of tau in quick flow will now become equal to, I have calculated this value, which is mu times capital U upon b plus, what is that value equal to? Recall the formula we have seen in the case of laminar flow between two fixed parallel plates. It was minus dP upon dx times b minus 2y whole divided by 2. This was the value. So I can see this is the value of shear stress in the case of wet flow, shear stress in the case of wet flow. So with this we have seen 4 formulas. One was regarding the value of velocity, one was regarding discharge, average velocity, and then shear stress. All these formulas were something like combination of simple wet flow and laminar flow between two fixed parallel plates. Only use the idea of addition of these two things, that is simple wet flow and laminar flow between plates, for these 4 formulas. For other things, please don't use that idea. That means, let me tell you that if you are thinking that the value of U maximum in the case of wet flow is equal to U maximum in the case of simple wet flow plus U maximum in laminar flow between plates, then this idea is perfectly wrong. This is wrong. To get the value of U maximum, now you'll have to use some mathematical logic. The idea is U maximum is going to be the value of local velocity at which the value of du by dy is equal to 0. This you have to do if you are supposed to find out the value of U maximum. You can treat this as a question for your homework. If you have difficulty, whenever we have doubt clearing classes, that time you can very well ask me this thing, how to develop the equation of U maximum. But I have given you the idea. In this you cannot go for combinations. Please be careful. Whatever 4 formulas I have given you for combinations, those are more than sufficient for your examination. If you want U maximum, go for this idea. Let us start questions on laminar flow topic. Let us take the first question. The question says a fluid of kinematic viscosity 0.4 Stokes flows through a 8 cm diameter pipe. Maximum velocity in the pipe for laminar flow will be how much? Now, the question has some given data. Given data over here is kinematic viscosity is given to you, that is nu is equal to 0.4 Stokes. 0.4 Stokes, if you convert it into SI units, you are going to get 0.4 into 10 power of minus 4 meter square per second. Fine, nu is given to you. Diameter is given to you as 8 centimeters. So you can say diameter is equal to 8 into 10 power of minus 2 meters. Now the question is asking over here, maximum velocity in the pipe for laminar flow is how much? Maximum velocity, he wants over here the value of U max is equal to how much? This is the question asked. Now how do we find the value of U max? Let us see that if it is laminar flow, we know that limiting Reynolds number or Re maximum has to be equal to 2000. This is what we know regarding laminar flow in pipes. Now we know that the formula for Reynolds number is rho V d by mu maximum has to be equal to 2000. Now since nu is given to me, what I'll do is I will club this rho and mu together. So I can write from here, I can also write from here that this implies V into d by nu maximum is supposed to be equal to 2000. It is supposed to be equal to 2000. Now the value of d and the value of nu is given to you already. That means the only thing that can be maximized over here is the value of velocity. So from here I can say that, from here I can say that the value of V maximum times d upon nu has to be equal to 2000, which implies the maximum average velocity of flow in laminar flow for this particular case is 2000 multiplied to nu upon diameter, or I can say 2000 multiplied to nu. We have just seen it is 0.4 into 10 power of minus 4 whole divided by diameter is equal to 8 into 10 power of minus 2. Now if you calculate this thing, you are going to get that the value of V maximum, happens to be equal to 1 meter per second. This is the value of maximum average velocity. Now for a moment, please look back at the question. What did he ask you? What was the question asking us? If you look over here, the question is asking us maximum velocity in the pipe. Now there are two possibilities. One is maximum velocity for laminar flow through pipe, that we have already found out. The other thing is maximum velocity in the pipe. Maximum velocity in the pipe. That means for this average velocity, what is the maximum local velocity is being asked. So we can say that the value of, we know that the value of maximum velocity, local velocity, has to be equal to twice the value of average velocity in the case of laminar flow. So I can say that this is going to be 2 times 1 meter per second, that is equal to 2 meters per second. This is the answer to the question asked. If he would just ask you what is the maximum velocity for laminar flow through pipe, then your answer would be this much. Fine. If he's asking you what is the maximum velocity in the pipe for the laminar flow, then he's talking specifically about local velocity, maximum local velocity. This is going to be the answer. Fine. After having seen this, let us go for the next question. Now this question over here, read the question for yourself. The question says the equation tau equal to minus dou p by dou x times r by 2 for flow through circular tube is valid for which flow? The options given over here are A, laminar flow only, B, turbulent flow only, C, uniform flow, D, laminar flow and turbulent flow. Now this question does not require a lot of discussion. It is a very basic question. We have already talked about this thing. Under fundamental concepts of flow through pipes, we have seen that if you are having a steady flow through pipe, then you are going to have tau equal to minus dou p upon dou x times r by 2 valid for any flow, whether it be laminar flow, turbulent flow or transition flow. Be it any flow, this particular equation is supposed to be valid, provided you are having a steady flow taking place over here. Fine. Now in this option, the answer should be option D, that is laminar flow and turbulent flow. Of course, option C is perfectly wrong. because you see none of these flows are going to be uniform flow. Now just imagine if you are having a uniform flow, then what would happen? The velocity profile is going to be uniform throughout. If the velocity profile at any section, let us say, is uniform, then there won't be any velocity gradient developed. If there is no velocity gradient, the shear stress should be zero. So straight away when I look at this question, regardless of getting correct answer, I can straight away eliminate of this thing. It should be the wrong answer. Of course, over here the answer is laminar flow and turbulent flow. Fine, after having seen this, let us go for the next question. The question reads, the discharge in meter cube per second for laminar flow in a pipe of diameter 40 mm having centerline velocity of 1.5 meters per second is how much? While solving such a question, look at the options first. There's a particular pattern in the options. You see, every numerator for these options is 3 pi. So try to get answer in that particular fashion itself. Fine, let us start with the given data. Given data. He has mentioned that the diameter is equal to 40 mm. So let us say diameter is equal to 40 mm. Since the answers are given in the form of ratio or fractions, I will write this in fraction, that is equal to 4 by 100 meters. The centerline velocity means U maximum. U maximum is equal to how much? 1.5 meters per second. Again in fractions, I'll write it as 3 by 2 meters per second. Now the question asked over here is, what is the value of discharge? Now you see, discharge we know is equal to pi by 4 d square multiplied to not the centerline velocity but the average velocity. Now recall that average velocity in the case of laminar flow through pipes is equal to centerline velocity divided by 2. We have discussed this thing. It is a very fundamental concept in laminar flow through pipes which you are supposed to remember. Fine. What I'm going to do now is, in place of V, I'm going to write U max by 2. So I have over here Q is equal to pi by 4 times d square multiplied to U max by 2. Now mind you, this is not a general equation for any flow. It is only valid in the case of laminar flow through pipes. Fine. Let us put numbers. So I have over here pi by 4 times diameter we were having was 4 upon 100 whole square, means again you are having a 4 upon 100 over here, multiplied to U max is equal to 3 by 2. So you have over here 3 by 2, again a 2 over here times 2. Now you see, I can cancel off a 4 from here and a 4 from here, a 4 from here and a 4 from here. So what am I remaining with? I am remaining over here with 3 pi upon 100 square, that is 1 followed by 4 zeros. 4 zeros. Now this is in units are meter cube per second. So 3 pi upon 10,000 is the answer. If you look at the options given over here, then the answer is supposed to be option D, 3 pi by 10,000. This was again a simple question. Let us move forward to the next question. The question now says that flow rate of a fluid, density being 1000 kg per meter cube, in a small diameter tube is 800 meter cube per second. The length and diameter of the tube is 2 meters and 0.5 mm respectively. The pressure drop in a 2 meter length is equal to 2 megapascal. The viscosity of the fluid in millipascal second is how much? This is a question asked. Now, regarding this question, solving it is quite simple, but I want to discuss something else. You see, today you are solving questions for laminar flow. You know the topic very well. It is for laminar flow. So you would straight away start with the equations of laminar flow. But let's say this question you are facing in examination. If you face such a question in examination, over there you do not know whether it is laminar or transition or turbulent flow. What would you do then? You see, questions like this have to be assumed as laminar flow unless any other thing is mentioned. Fine. Later, if you have any doubts regarding your assumption, you can verify your assumption by doing cross-checking. Let us say you can find out Reynolds number later on. Again, you can check. So what I'm going to do now is I'm going to assume that the flow is laminar and I'm going to start. Let us start with the given data. Given data. Density is mentioned. Density is equal to 1000 kg per meter cube. Diameter is equal to, I'll be writing in SI units, 800 mm cube per second. So you're having 800 into 10 power of minus 9 meter cube per second. Next, length is equal to 2 meters and diameter is equal to 0.5 mm. So I can write it as 0.5 into 10 power of minus 3 meters. Pressure drop in 2 meter length is equivalent to 2 MPa. So delta P over here is equal to 2 MPa, that is 2 into 10 power 6 Pascal. This is a value of delta P we are having. The viscosity of the fluid in millipascal is how much? So the question is, you are supposed to find mu is equal to how much? And the units you are supposed to find it in are millipascal second. These are the units in which you are supposed to find out the value of mu. Let us start solving the question. If I assume that the flow over here is laminar flow, then I can say the value of discharge is equal to, we have formula, it is equal to pi by 8 mu into minus dp upon dx multiplied to capital R power 4. This is the value we have. Now you can rewrite this in the form of pi upon 128 mu, pi upon 128 mu into delta P upon L multiplied to d power 4. Now let us start writing in numbers over here. So this value is equal to pi. I want to find out over here the value of viscosity. So I can say instead mu is equal to pi upon 128 times q multiplied to delta P by L times d power 4. Let us put in numbers now. We know that Q is equal to 800 in 10 power minus 9. So I put over here 8 into 10 power minus 7, same thing. Delta P is equal to 2 into 10 power 6 So you have 2 into 10 power of 6. Length is equal to 2 meters. Length is 2 meters. D power 4, diameter is equal to 0.5 into 10 power of minus 3 whole power of 4. Now you calculate all these things, you are going to get mu is equal to 1.92 into 10 power minus 3 Pascal second. Since we have taken everything over here in SI units, you are going to get the value of mu also in SI units. Since the question is asking about millipascal second, I can now say the value of mu therefore has to be equal to 1.92 millipascal second. This is the value of mu we are having. Now let us move further. Achha, what you can do over here, one more thing is, after getting this answer, it's not required in general examinations, but let us say such questions are asked in some conventional type of examinations. That time, taking this value of mu, density, diameter and velocity you can find out using discharge, find out the value of Reynolds number. Once you find the value of Reynolds number, if you are getting the value of Reynolds number less than 2000, you can then mention that the assumption we made that the flow is laminar is correct. If the value is more than 2000, and that is not going to happen in these cases, if the value is more than 2000, then the assumption we have made over here is wrong. You would require some more data then in order to find out the value of viscosity, because when it comes to turbulent flow, we do not have such simple formulas. Anyway, moving further to the next question. Let us see the question. The question says, in a laminar flow through a circular pipe of diameter 200 mm, the maximum velocity is found to be 1 meter per second. By maximum velocity, we mean over here centerline velocity. Then the question continues, says that the velocity at a radial distance of 50 mm from the axis of the pipe in meters per second is how much? Very basic question. Now, let us write the given data again. The question says that you are having a pipe of diameter 200 mm, diameter equal to 200 mm. Diameter equal to 200 mm implies that the capital R, that is the radius of the pipe, is equal to 100 mm. Fine, 100 mm. And it further says that the centerline velocity, that is U maximum, is equal to 1 meter per second. I hope you are observing all these questions. I am writing given data separately. The reason being, remember this thing, whenever you are having questions which depend purely on formulas, in those questions it is a healthy habit to write with given data first. Okay, start with given data first. The reason is, once you are having given data in front of you, you will get an idea of which formula to use. You see, in this chapter, most of the questions are formula based. They are not analytical questions, purely formula based questions. So better start with given data. If you are having analytical questions, then you have to first analyze, think over the question and then decide what to do. Over there, given data might be important, but not as important as we are having over here. Moving further, the velocity at a radial distance of 50 mm from the axis of the pipe is how much? So what do we have to find? We are supposed to find over here the velocity, local velocity at a radial distance of 50 mm. This is the question asked. Very simple question. The question has already mentioned that the flow is laminar. Now we know that in the case of laminar flow, we are having a particular formula which relates local velocity to maximum velocity. And how do we get that? I hope you recall local velocity is equal to maximum velocity times 1 minus capital R square upon, sorry, small r square upon capital R square. This is the relationship we have. We have seen this relationship when we have derived the concept of velocity in the case of laminar flow. Now let us push in numbers over here. So you have local velocity u is equal to u max is given as 1. Center line velocity is 1 times 1 minus. I can write it as r upon capital R whole square. So I'm having small r as 50 upon capital R as 100, this thing squared. Fine. 50 upon 100 is equal to 1 by 2. 1 by 2 square is equal to 1 by 4. So you have over here u is equal to 1 times 1 minus 1 by 4. 1 minus 1 by 4 is equal to 3 by 4. So you can see that the local velocity at this particular position is equal to 3 by 4 meters per second, or it is equal to 0.75 meters per second. This is the value of local velocity we are having. Again, a simple question. Okay, most of the questions you are seeing over here are worthy of 1 mark in GATE examination or can be asked in IES examination. Let us move further. The question says now, oil having a relative density of 0.1 and viscosity 1 poise is flowing through a pipe of 50 mm diameter with a velocity of 2 meters per second. Darcy friction factor for the flow is how much? Now this is a question on Darcy friction factor. Again, let us start with given data. Given data. Relative density is given to us. That is, the value of S is equal to how much? 0.8. This is mentioned. If S happens to be 0.8, that means the density over here has to be equal to 800 kg per meter cube. 800 kg per meter cube. Next, viscosity is 1 poise. We know that 1 poise is equal to 0.1 Pascal second. 0.1 Pascal second. And the diameter is 50 mm. So let me write over here capital D is equal to 50 mm, or I can say 0.05 meters. 0.05 meters. And you are supposed to find over here Darcy friction factor. To find Darcy friction factor F. Let us see how do we start this question. I'm not going to straight away write that the value of F is equal to 64 by RE. That, even though is correct in this case, but is not the proper way of approaching this question. What I'm going to do is, first I'm going to identify the value of Reynolds number. Once I get Reynolds number, once I confirm that the flow happens to be laminar, only then will I put in the formula as 64 upon RE. I hope you're following. So let us start with the formula for Reynolds number. We know that Reynolds number is equal to rho Vd by mu. So if I put in the numbers over here, rho happens to be equal to, velocity also is given. I'm sorry, I have missed one given data over here. Velocity is equal to 2 meters per second. I'll be using that as well. So I'm having 800 over here times 2 times diameter is equal to 0.05 upon mu is equal to 0.1. Now, if you see this thing, 2 times 0.05, this entire thing itself is equal to 0.1. So I can cancel this entire thing out. So now I get that the value of Reynolds number is equal to 800. I am assured that the flow is laminar since this value of Reynolds number is less than 2000. It is less than 2000. I am confirmed that the flow happens to be laminar. If the flow is laminar, now is the time of me putting in the formula of F as 64 upon Re. 64 by Re. That is 64 upon Re is equal to 800. So 800. There is no need of calculator for this thing. It is quite a simple calculation. You see, if you divide throughout by 8, you are going to get 8 over here and 100 over here. So 8 by 100 we know is equal to 0.08. This is the answer to the value of Darcy friction factor. Let us move further to the next question. Achha, one more thing. If the value of Re, if you get the value of Re beyond, let us say 4000, you would require the formulas for turbulent flow. Those formulas we'll be seeing in turbulent flows chapter. Let us go for the next question now. Now this is a question on ratios, and let me tell you, these kind of questions have appeared multiple times in various examinations. Read the question for yourself once. The question says, consider a fully developed laminar flow in a circular pipe if the diameter of the pipe is halved while the flow rate and length of the pipe are kept constant. The head loss increases by what factor? Fine. It's a question on ratio. Over here, he's talking about head loss. So let me straight away start with the concept of head loss. The formula for head loss in the case of laminar flow, he has mentioned that the flow is laminar. Flow is laminar. We know that in the case of laminar flow, we are having the formula of head loss as 128 mu QL upon gamma times pi times d power 4. At any instant you feel that you don't remember the formula, don't worry. I have talked about how to get the formula by knowing very few formulas also. From there also you can get this thing. As a matter of fact, when I was starting to write the formula, for a moment I felt that I don't remember it, but still, if you recall some basic formulas, you can get this very easily. Now, head loss is equal to 128 mu QL upon gamma pi d power 4. This is the formula for head loss in the case of laminar flow only, mind you. Now, the question says that the diameter of the pipe is halved while the flow rate and length of the pipe are kept constant. So, you see, discharge is being kept constant. Discharge is being kept constant, let us say, and length is being again kept constant. The only thing is the diameter is being halved. So I can write over here the value of D2 is equal to D1 upon 2. Head loss is going to increase by what factor? So he wants to do here the value of head loss 2 upon head loss 1. Now please observe, the fluid you are using is the same. That means the value of mu and gamma are not going to change. The question itself has mentioned that Q and L are being kept constant. 128 and pi are by nature constants. That means the only thing I have to worry about over here is the variation of head loss with respect to diameter. So I can start writing over here. This implies head loss is proportional to 1 by d power 4. Head loss is proportional to 1 by d power 4 because rest everything happens to be a constant over here. If so, the value of H2 upon H1 has to be equal to D1 upon D2 whole power 4. Whole power 4. So in this case, it is going to be equal to Now d1 is d1 itself. The value of d, if you see over here, we have got as d1 upon 2. So I can write d1 upon 2 whole power 4, which gives me the value of h2 upon h1 as 2 power 4. And 2 power 4 is an oral value, it is equal to 16. So the answer to the question over here is head loss is going to increase by a factor of 16. This is the answer to the question. And let me again tell you that these kind of questions are extremely important. I myself, while studying also, have seen questions like this plenty of times in various examinations. Be it GATE examination or IES or ISRO, any kind of exam, competitive examinations will come across. You will be seeing these questions in plenty in flow through pipes. Let us further go to the next question. The question says, an oil of viscosity 10 poise flows between two parallel fixed plates which are kept at a distance of 50 mm apart. Pressure drop over the length of 120 centimeter is observed to be 3 kilopascal. The width of the plates is 0.2 meters. The discharge of flow in liters per second is how much? Now this is a question not on flow through pipes, it is rather a question of flow between two fixed parallel flat plates. Let us start with given data. Given data over here. Oil of viscosity 10 poise. So viscosity he has given to you already as 10 poise, that is equal to 1 Pascal second. Viscosity 1 Pascal second. The plates are kept at a distance of 50 mm from each other. Now if you recall the nomenclature, we represent the distance gap between the two plates by capital B. It is equal to 50 mm, that is equal to 0.05 meters. Fine. Pressure drop over a length of 120 centimeters. So L over here is equal to 1.2 meters. 1.2 meters. And over this length he has given the value of pressure drop as 3 kilopascal. That is equal to 3 into 10 power of 3 Pascal. Fine. The width of the plates is equal to 0.2 meter. Width of the plate is given by W, that is equal to 0.2 meters. Fine. The discharge of flow in liters per second is how much? So over here we are supposed to find out the value of discharge. Q is equal to how much? This is the question that has been asked. Let us see how to solve this question. I hope you recall that the formula for discharge in the case of laminar flow between two fixed parallel plates is given by Q is equal to 1 by 12 mu minus dP upon dx multiplied to B cube times W. This is the formula we are having for discharge between two fixed parallel plates provided the flow is laminar. Again, I have to make a standard assumption over here that the flow is laminar only. Fine. Now, I can replace the value of minus dP by dx by delta P by L also. That means I can say it is 1 by 12 mu times delta P upon L times B cube into W. This is the value of Q. Put in the numbers now. If I put in the numbers, I am going to have Q is equal to 1 by 12 times mu is equal to 1. So 1 over here. Delta P is equal to 3000. length is equal to 1.2, length equal to 1.2, b cube is 0.05 whole cube, so 0.05 cube, and width is equal to 0.2, width is equal to 0.2. If you put in all these numbers together, you are going to get the value of discharge is approximately going to be equal to 5.2 into 10 power minus 3 meter cube per second. Now this is the answer in meter cube per second, but if you recall, the question was asked for discharge in liters per second. So I can say this is equal to 5.2 liters per second. This happens to be the answer to the question asked. Let us move further to the next question now. Question says, consider a steady, fully developed flow in a horizontal pipe of diameter capital D. Over a section of length of this pipe, a pressure drop of delta P is observed. Fine. The average wall shear stress over this section is equal to how much? Now this is a very basic formula. He is asking you directly the value of the formula. So now this is a case of fully developed flow in a horizontal pipe. Since he's talking about wall shear stress over here, you don't have to worry about which flow it is, whether laminar or transition or turbulent. In all the cases, the formula for shear stress remains the same. Let us see. We know that the formula for shear stress at the wall is equal to minus dP upon dx multiplied to capital R upon 2. Now this is the answer. But if you look at the format of the options over here given, okay, he has not given you in the form of what do you call minus dP by dx. He has preferred over here delta P. Next, again he has not preferred radius, he has chosen diameter for his options. So let us say that minus dP by dx can be replaced by delta P upon L, and R we know is equal to diameter by 4. Put in these values, so now you would get the value of tau naught is equal to delta P upon L times D by 4. Look at which option is suitable for this thing. Delta P times D upon 4L. Option A itself would be correct over here. So this is very basic question, you see. Okay. Let us take the next question. Now this question is a previous GATE examination question which has appeared for 2 marks. 2 marks, and we are going to avoid using calculator over here, hopefully. Let us see the question. Oil of density 800 kg per meter cube and viscosity 0.1 pascal second flows through a circular inclined pipe of diameter 1 centimeter with an average velocity of 0.1 meters per second. The pipe makes an angle of 30 degrees with the horizontal. If the oil flows in the upward direction, determine the pressure difference between the 2 points which are separated by 10 meters along the pipe. Fine. He has further allowed you to prefer the value of G as 10 meters per second square. Mind you, whenever he says use G as 10 meters per second square, take it. Fine. Do not go back to the actual value, because in this particular question, choosing the value of 9.81 for G was giving a particular value, and that value was beyond the scope of the answer, the key answer in GATE examination. So whenever he says take G as so and so, prefer that only. Okay. Let us see. We have to draw a diagram over here before writing the given data. Okay. So fine, let us say that you are having a pipe. When solving questions, what I prefer is a line diagram for a pipe. Let us say this is a pipe you are having. Oh, let me, 1 second. Let us say this is a pipe you are having. Suppose this is some section 1 and this over here is section 2, and the length along over here, the length is equal to 10 meters. The length is equal to 10 meters. Furthermore, it is given that the angle made over here is equal to 30 degrees. The angle made is equal to 30 degrees. Fine. Whenever I see these kind of questions, what I do is I make it a point of mentioning the value of datum difference. Now this over here is Z2 minus Z1. What would the value of Z2 minus Z1 over here be equal to? Now think logically. It would be equal to 10 sine 30, is it not? It should be equal to 10 sine 30. So I can say over here, this is equal to 10 sine 30 degrees. That is equal to how much? 5 meters. The value of delta Z is equal to 5 meters. Also mentioned that the flow is taking place in the upward direction. This is the direction of flow taking place. Furthermore, he has given you some data. What is the given data apart from this? He has given you density over here, diameter over here. Let us see what are the values. Density is 800, viscosity is given, diameter 1 centimeter, viscosity 0.1 Pascal second, and average velocity. So let me write. Density is given as 800 kg per meter cube. 800 kg per meter cube. Diameter is given as 1 centimeter, that is equal to 0.01 meters. Average velocity is equal to 0.1 meters per second. So average velocity and viscosity also is given. Average velocity is equal to 0.1 meters per second, and viscosity over here is equal to 0.1 Pascal second. 0.1 Pascal second. The question is asked over here regarding the value of pressure difference between the 2 points, that is delta P or P1 minus P2 is equal to how much? Drop in pressure is equal to how much? This is the question asked. This is the question. So let me do one thing. Let us start solving the question. Now, he's asking the value of P1 minus P2 or delta P over here. First thing I'm going to do is, I'm going to find out whether I'm having a laminar flow at hand or not. I can't directly use the formulas. So let us start with checking whether the flow is laminar or not. So I'm going to start with Reynolds number. Re we know is equal to rho Vd upon mu. Now this is going to be equal to density we know is equal to 800 velocity is 0.1, diameter is 0.01, then mu is equal to 0.1. If you calculate this value, the Reynolds number would be equal to, the value of Re would be equal to 8. Now this is for sure laminar flow. So let me save this as some equation number 1. Fine. After confirming that the flow is laminar, I am having the liberty of choosing the formulas for laminar flow. Which formula shall I write? I can write over here the formula of delta P. I know that the formula of delta P is equal to how much? It is equal to 128, or if I want to write velocity, I can write 32 mu VL upon d square. This is the formula for delta P. But this formula is applicable provided I'm having a horizontal pipe. In this case, since I'm having an inclined pipe, I am supposed to write over here delta P star. This is a formula for delta P star. Let us put in the numbers and find out this value. This is going to be equal to 32, mu is equal to 0.1, V is again equal to 0.1, L is equal to 10, L is equal to 10 whole divided by d square is equal to 0.01 whole square, 0.01 whole square. If you calculate this value of delta P star, you are going to get delta P star is equal to 32,000 pascals, or you could say it is equal to 32 kilopascals. But again, this is not what is being asked. We are being asked the value of delta P. We are being asked the value of delta P. What I can do now is, I can say delta P star over here, is equal to, it is equal to P1 star minus P2 star, which is equal to P1 by gamma, P1 plus rho g z1 minus P2 plus rho g z2. This is the value we are having right now. Since we only want the value of P1 minus P2, so I can say, this is equal to delta P star. Let me write over here. Since I only want the value of P1 minus P2, I can now write down P1 minus P2 is equal to delta P star plus rho g into Z2 minus Z1. So basically what I'm doing is, I'm taking this term as well as this term on the right hand side. I'll be getting this thing. Now delta P star we already know it is equal to 32,000 Pascal. So I can write now 32,000 Pascal along with rho over here is equal to 800. Now comes the importance of the assumption made. G is equal to 10 times Z2 minus Z1 is equal to 5. So you're having 8,000 times 5, that is equal to 40,000. Add it to 32,000, that is going to give you 72,000 Pascal. This is the value of delta P, or in kilopascals it is equal to 72 kilopascal. This is the answer. This is the value of answer to the question asked over here. The answer 72 kilopascal over here. Now, this is one way of approaching the question. Please look at it again. You are starting with first confirmation whether it is laminar flow. After it is confirmed the flow is laminar, next thing you went down to find out piezometric pressure difference. From piezometric pressure difference you are getting static pressure difference. The reason for piezometric pressure difference was because the pipe was not horizontal, it was rather inclined. Okay, if it was horizontal, then you would not have to go for piezometric. Piezometric itself would be the static pressure difference then. Now, this is one way of approaching the question. There is one more way, which is more basic method, which I prefer, and that is by using basic Bernoulli equation along with Darcy friction factor equation. Let us see how do you find out the value of delta P from there. What I'm going to do now is, again I'm going to take this diagram, extend it. Let us see. Now look at this. I'm looking for an alternate method to solve the question. Alternate method to solve the question. And this is a better method, a more refined method, I would say. Again, it is going to start with finding out which flow you are having. If you are having over here laminar flow, then you would have to find, first of all, Reynolds number you would have to find out. Since we have already found it is equal to 8, I am straight away writing. Once you get that the flow is laminar, find out the value of friction factor. Friction factor we know is equal to 64 by Re in the case of laminar flow. So put in the numbers, you are going to get 64 upon 8. That means the value of friction factor itself is equal to 8. Fine. Save this thing, very useful. Let us say some equation 3 we are having over here. Fine. After getting the value of friction factor, next thing is I am going to find out the value of head loss. We know that head loss is equal to FLV square by 2GD. And where am I getting this from? I am getting this from Darcy-Weisbach equation. So I can say over here this is equal to 8 into 10 into velocity is equal to 0.1, so 0.1 square divided by 2 times 10 times 0.01. Very simple calculations. 10 cancels 10, 0.1 square is cancelling with 0.01, 2, and I'm left only with a 4. So the value of head loss over here is equal to 4 meters of fluid, let us say. 4 meters of fluid. Let me save it as some equation 4. Now comes one more basic equation, which is Bernoulli equation. According to Bernoulli equation, I can write over here P1 by gamma plus V1 square by 2G plus Z1 has to be equal to P2 by gamma plus V2 square by 2G plus Z2 plus head loss. This is the equation we are having. Now, since the pipe is having a uniform diameter throughout, I can say that the velocity at section 1 and velocity at section 2 both are the same. The question is asking you about the value of P1 minus P2. So what you can do over here is you can write P1 minus P2 whole divided by gamma is equal to Z2 minus Z1 plus head loss. Furthermore, you can say the value of P1 minus P2 is equal to gamma times Z2 minus Z1 plus head loss. This is the value of P1 minus P2 you are having. Now, the value of gamma we know is equal to how much? It is equal to 800 times G, that is density times G. So this is the value. Z2 minus Z1 is equal to 5. Head loss is equal to 4. This value comes out to be equal to, now if you check, 8 times 9 is 72 followed by 3 zeros. So 72,000 Pascal. If you want to write the answer in kilopascal, you would get the value of P1 minus P2 or delta P is equal to 72 kilopascal. Either way, you are getting the same answer. So whenever these kind of questions are asked you, you can use either approaches. Let me brief you. The first approach, we were not using Darcy-Weisbach equation. You see, when you use Darcy-Weisbach equation to get the value of head loss, in that case, you can go back to Bernoulli equation. The reason is, in Bernoulli equation, the limitation we are having in general is we do not know the value of head loss. Once you know the value of head loss, then Bernoulli equation can be easily used. These were some questions, some basic questions in the case of laminar flow through pipes and between plates.